Well, I think it is 10:30 here in the East Coast, so it is time to begin. So without further ado, I will get started. Welcome, everyone. My name is Duncan Lorimer, and on behalf of myself and my two co-organizers, Bing Zhang and Vicky Caspi, it's a real pleasure to kick off the first of two sessions on our topic entitled, What Can We Learn from a Growing Sample of Fast Radio Bursts? Really like to thank you all for being here. Big thanks to all of our speakers that we've got coming up in both sessions this week for what will be a very exciting program. We're running things over Zoom, of course, as we're all used to these days, and I'm going to be communicating with the speakers during this session via chat messages to remind them of their time. So we've got 6 invited speakers. The program is a little more detailed than is what is available online. I will post a link to that, or Vicky, if you can post a link to the Google Doc in the chat, people can take a look at that. In any case, for the invited speakers, I'll message them after 12 minutes just to let them know that there's 5 minutes of their talk left. They've got 17 plus 3 minutes of discussion. And after 7 minutes of the contributed talks, and we've got 5 contributed talks, I'll message those speakers that their 10 minutes of talk time is coming to an end, and they've got 2 minutes of discussion. We might have a little bit of time for general discussion at the end of the session. And the way I think that we'll proceed with the questions is just drop them in the chat during the talk, and I will just read them out on your behalf just to speed things along at the end of each speaker's presentation, and we'll get through as many as we can in that discussion time. So just as a reminder, of course, just don't forget to mute yourself unless you are the speaker or really need to speak, but preferably just mute yourself to avoid feedback. So thanks everybody again. And Vicky, do you have anything to add before we get started?
No, I don't think so. I just want to, well, thank you, Dunk and Bing co-organizers, and the Marcel Grossman organizers for the meeting. And thanks to all the speakers. And I'm really, really excited to hear some of these talks.
Great. So yes, without further ado, I'm going to call upon Manisha Caleb to kick things off. She's going to give us an invited talk entitled Searching for Fast Radio Bursts with Meerkat. Manisha, if you want to go ahead and share your screen, I will give you a reminder after 12 minutes.
Sounds great. Thanks, Tom.
Yeah.
All right, good afternoon, everyone. Today, I'm going to be talking about searching for FRBs with Meerkat. Since I'm kicking off the session, I thought it would be good to start off with a brief introduction to FRBs to sort of set the scene for the rest of the session. So simply put, fast radio bursts, or FRBs, are bright millisecond duration radio bursts of as yet unknown origin occurring at cosmological distances. We know that anywhere between 5,000 and 10,000 of these bursts go off randomly in the sky every day, and the characteristics suggest that they're the consequences of some of the most energetic processes in the universe. What makes FRBs special are their very large dispersion measures, or DMs. Now, DM is simply an electron counter for any given line of sight, and it manifests itself as this beautiful frequency-dependent arrival time of the signal shown by the quadratic sweep in the prototypical Lorimer burst figure that you see on the right here. The observed values of DM are much larger than what can be accounted for by our own galaxy, suggesting extragalactic origins for these bursts. FRBs are mostly observed as one-off events, but a small fraction of them have been observed to repeat, which has led to an apparent dichotomy in the population. Some FRBs have been localized to host galaxies, either through the repeat bursts in the case of repeaters, but also through interferometric techniques, upon discovery for one-off events, and the redshifts for these go up to about 0.6. But FRBs do potentially also arise at much higher redshift galaxies, primarily because we observe them at much larger DMs. FRBs have been detected all the way from 110 megahertz up to about 8 gigahertz, but we've never really seen them simultaneously across a wide frequency band, and this is due to their varying spectral indices, which we see even between consecutive bursts separated by milliseconds. Also, we don't know whether they emit outside this frequency range just yet. Their estimated high radioluminosities required to produce such extreme events at cosmological distances is perhaps what makes them most tantalizing. The observed DM is typically a combination of various contributions along the line of sight, as you can see from the equation in the bottom here. So the signal bears the imprint of the medium that it travels, and as a result, it encodes information about everything along its path. So it tells you something about the progenitor source and its environment, the host galaxy, the intergalactic medium, the intercluster medium, the circumgalactic medium, as well as the interstellar medium of our Milky Way. So essentially, it tells you, or rather it's a record of the magnetic field strength, as well as the turbulence that it encounters during its passage. Now, we've got a fairly good handle on the DM contribution from the Milky Way based on pulsar observations. So once you subtract this component, what you're left with is an unknown IgM host and source contribution. But with the advent of routine localizations, we're sort of able to account for the contributions from the host and the source, which leaves us with just the IgM, or the cosmic contribution to the DM. And as a result, FRBs are expected to be excellent tools for cosmological studies. The extragalactic nature is better visualized here. So you've got an all-sky distribution of the published FRBs, and this figure sort of nicely filled up once the CHIME catalog came along. The background color map is the electron density content of the Milky Way. The white dots are the pulsars, and the colored markers are the FRBs themselves. Now, the FRBs also follow the same color map in the background. And we see that on average, an FRB has an observed DM of about 500 units, of which only about 10% is the galactic contribution. And also we see FRBs are isotropic, so they don't really have a galactic latitude dependence, which is kind of what we expect for extragalactic events. Overall, the FRBs observed to date, they show a diversity of observed properties, and these are both intrinsic as well as extrinsic properties. We know of about 600 FRBs, of which about 20 have been seen to repeat. But whether all FRBs repeat is still very much an open question. Interestingly, there does not seem to appear any significant differences in the underlying dispersion measure or fluence distribution of repeaters and non-repeaters as seen by the CHIME sample. And I'm sure we'll hear more about this from Pragya later on in the session. Polarization information is available for a handful of FRBs, and they're quite diverse. So it's sort of a mixed bag in terms of polarization. Repeater pulses are seen to be broader in duration, so they last longer, as well as spectrally limited in terms of bandwidth. And this again is from the CHIME sample of about 550 sources of repeaters and non-repeaters. Now, this could either be due to propagation effects or intrinsic to the source itself. Repeaters also seem to exhibit what we now refer to as the SAT trombone feature, which is shown in the figure on the right here. So you see that the signal drifts or cascades down towards lower frequencies at later times within the burst envelope. Now, this feature is more common in repeaters than non-repeaters, and is probably some combination of the emission mechanism and line of sight propagation effects. It might just be that this drifting substructure feature is predictive of repetition, but that's something that's still being investigated. Now, these observational properties, particularly the spectrotemporal and polarimetric properties, they provide us with valuable information about the progenitor as well as the propagation medium. And you can sort of combine the information you get from these to constraint theories. Now, firstly, the combination of the duration and the light travel time suggests that they arise from compact emission regions. Despite several campaigns, no simultaneous high energy counterpart to an FRB has been detected yet. That is, of course, with the exception of the FRB-like pulse from the galactic magnetar 1935, which was detected at high energies. So it appears that the sensitivity of current instruments could be the bottleneck in terms of distant FRBs, but with more closer FRBs being discovered at megaparsec distances, it might not be too long before we do actually detect a high energy counterpart to an FRB. We know that they're coherent emitters based on their high brightness temperatures, and the fact that we've detected them all the way down to 110 megahertz implies an optically thin medium for the radio wave to propagate. Additionally, a couple of prolific repeaters, which have been monitored extensively over the years, have been seen to exhibit long-term periodicity. So they have 16 days as well as a 160-day period. So this suggests systems in a binary or precession or maybe even spin periods. Also, the locations of FRBs within their host galaxies suggest core collapse supernovae and short gamma ray burst progenitors, both of which can produce neutron stars and magnetars. So based on all this information, the leading models for FRBs involve neutron stars, particularly pulsars and magnetars. But despite all these constraints, the progenitors of FRBs still remain a mystery, and many major radio telescopes around the world are currently undertaking large area surveys as well as targeted searches at radio frequencies from 100 megahertz all the way up to tens of gigahertz to discover, study, and understand the origins of these FRBs. Now, MEATRAP is one such project at the Meerkat Radio Telescope in South Africa, and Meerkat is a precursor to the SKA. Meerkat is an array of 64 dishes, so each dish is about 13.96 meters in diameter, and the entire array is spread out over 8 kilometers in the Karoo region in South Africa. The table here gives you the specs for the telescopes. Meerkat operates at UHF band and L band, and currently S-band receivers are in the process of being fitted at the telescope. Meerkat's very flexible, which means subarrays can be formed with a maximum of 4 with 16 antennas each, and the commensality allows for projects to efficiently piggyback one another. MEATRAP is an ERC funded collaboration led by Ben Stappers at the University of Manchester. It is a fully commensal project, which means that we piggyback all the Meerkat large survey projects which have been allocated time at the telescope for various science goals. And consequently, this gives us unprecedented on-sky time. So we have tens to thousands of hours over the course of about 5 years. The neat thing about this project, though, is the Mueller Optical Telescope. So it is a 65 centimeter fully robotic optical telescope in Sutherland in South Africa. And it co-points with Meerkat during nighttime observations. So what this means is that during nighttime, we have simultaneous optical data, which is excellent if you want to be able to detect contemporaneous optical flashes for an FRB. We have a total of 8 large survey projects that we piggyback off. And in particular, I should mention TRAPM and Thundercat. Now, TRAPM is also an FRB search program, but unlike MEATRAP, it is not commensal. Thundercat is the image plane transients program for Meerkat. So while running commensally, Thundercat will look for events that last greater than a second, while MEATRAP will look for events that last less than a second. And this is an excellent synergy while looking for FRBs because we will have simultaneous imaging data in this case. But having said that, we do have imaging data for all the LSPs that we piggyback. The figure on the left here shows the area that we've covered so far. So the darker the color, the more time we've spent on that field. The figure on the right shows our expected sky coverage over the course of MEATRAP. And as you can see, we've mostly been piggybacking galactic observations, which corresponds to the MEATime project in yellow here. And this bias is because we started piggybacking most other projects only late last year, so about October 2020. We expect our sky coverage to improve significantly for high latitude regions in the coming months. Meerkat observes simultaneously in 2 modes with MEATRAP. So we've got the incoherent mode and the coherent mode. In the coherent mode, MeerKAT uses the innermost 40 dishes of MeerKAT to form hundreds of beams on sky. And the field of view basically just depends on the overlap between the beams. And the coherent beam overlap is shown by the square in the center of the figure here. So this particular mode offers localization of tens of arc seconds or less, depending on the signal to noise of the transient, as well as the overlap between the beams. I should note that the number of beams is purely limited by compute resources that we have on hand, and currently we form 780 beams on sky. In the incoherent mode, the intensities of all 64 MeerKAT dishes will be added to create a less sensitive but much wider field of view of about 1.3 square degrees. And that is shown by the larger circle here. We've also got the Meerlicht field of view of 2.7 square degrees for comparison. A neat feature of this coherent beam tiling strategy is that we can form individual beam tiles at different locations within our incoherent beam. Now, a tile is simply a group of coherent beams that are clustered together. And this is nicely shown in the figure here on the left, where we formed 3 separate tiles on 3 different pulsar positions within our incoherent beam. So these are shown by the blue markers. You can't really see it here, but each marker is actually a tile of several beams that overlap one another. An advantage of this feature is that whenever we piggyback a field which has several interesting sources in it, we can form tiles on each of these sources. The figure on the right shows the beam tiling for varying degrees of overlap. The bottommost tile is 90% of the peak power. The second from bottom is half power, and then so on. So larger the overlap, the smaller the fraction of the incoherent beam that you cover, but the better the localization from the overlap. So we basically see that at 90% overlap, the beams are much closer together, covering only about 0.3 square degrees. And this will allow arc-second localization because you get multi-beam detections. But because there's a trade-off between how widely you can space your coherent beams and the localization you get from multi-beam detections, we chose to go with 25% overlap. This basically means that the edges of the coherent beams overlap at 25% of the peak power. So here's a schematic of our search pipeline. We search over a DM range of 0 to 5,000, and we look for a peak in our time series for each DM trial DM value. We use the Cheetah SK single pulse search pipeline for our searches, which runs AstroAccelerate, which is a highly optimized GPU-based single pulse search algorithm, and it's similar to Heimdall. The candidates from AstroAccelerate are then sifted and clustered in time based on some threshold criteria and fed into our machine learning classification system called FRBID. FRBID is based on fetch. So only those candidates which are labeled as real by the classifier are vetted by I. And currently we are only quasi-real time in our searches. So now for some science results. We've been fully operational on Sky for a little over a year now, and we've discovered about a dozen FRBs and 24 galactic transients. The DMs of our FRBs range from about 430 to 2,000 parsecs per cubic centimeters. 4 of our FRBs are incoherent beam only detections, which means that they could have occurred anywhere within our primary beam. That is to say, it's anywhere within 1.3 square degrees, but outside our coherent beam tiling. And you can see that we can't really say where the FRB would have occurred if it was an incoherent beam only detection. So we can't get that information from just the beamform data. But I should note, we do have simultaneous correlation data products for all our images, for all our observations. And the typical integration times of these are 8 seconds and 2 seconds. So if our FRBs are bright enough, then they can be detected in our 8-second or 2-second images to get arc-second localizations. Some of our other FRBs, which were detected in only our coherent beams, have been localized using multi-beam detections because of the overlap. Our FRB3 was detected in only one coherent beam. The pulse is shown in the figure here. We've got the spectrum as well as the DM transform. So this basically tells you the DM at which your signal to noise is maximized, which in this case is about 430. We also see a faint hint of another pulse at about 0.2 seconds after the primary detection, which suggests that this might be a repeater. Based on the fact that we didn't see it in any of the neighboring beams, we constrained the position or the localization error to smaller than the size of a coherent beam, which is shown by the sign contour here. Now, a coherent beam is about 45 arc seconds, and the localization region here is tens of arc seconds. We have 2 or 3 galaxies in there, and multi-wavelength analysis is ongoing. Frb 8 was detected in our incoherent beam, as well as a couple of coherent beams. And based on the ratios of the signal to noises and the point spread functions of the beams, we constrain the localization region to a narrow ellipse shown here. Now, there are a couple of galaxies in here, and so this image is from the Gemini South, taken with help of our collaborators, and we're in the process of obtaining spectra for these galaxies. Another exciting detection was Frb 6. So this was an extremely bright burst, so it was detected in our incoherent beam, as well as several hundred coherent beams at the same time. It was also bright enough to be detected in our 8-second images. The plot, well, you see the profile at the top, and then we've got the radial localization in the bottom. So this is the off-pulse image on the left and the on-pulse image on the right. The pixelization is just because the resolution was reduced to speed up the imaging. Multi-wavelength analysis and observations for the host galaxy of this is ongoing. And finally, the last Frb I'm going to talk about is Frb 7. So this again was seen only in our incoherent beam, but was bright enough to be detected in our 2-second images. The top plot again shows the pulse profile, and the bottom shows the off and on pulse regions for the Frb detections. I should note that we are working on the image quality for this particular detection. What was interesting about this Frb is that it was detected in a field with 2 other known sources within 1 square degree. Multi-wavelength analysis for this host galaxy is also ongoing. So in summary, I think with all these new projects like Aperitif and Chime and Meerkat and ASCAP coming online, we're now at a point where radical changes happen in the field on just a time scale of a few months. With the potential of multi-wavelength detections and the uses as cosmological probes, Frbs have kind of formed a bridge across several areas of astronomy. And there's a lot of potential for high impact science, not only in transient science, but also in cosmology. Thank you.
Thanks very much, Manisha. This is a great talk and a great way to start off the session and our little meeting. Nobody has dropped any questions in the chat. Please feel free to do so, or we've probably got time for one quick question. If anybody wants to just unmute themselves and ask directly, that's fine as well.
Hi, Yuri here. Misha, that's exciting.
Hi, Yuri.
For the imaging localization, of course, the UV coverage of Meerkat's pretty good. So was it relatively straightforward to identify the proper localization, or were there side lobes that potentially could be the source?
For most of our Frbs that have been localized, we have been able to get fairly straightforward localizations. But we did have issues, like I showed for Frb 7, we did have some issues with artifacts at our phase center. So we're currently investigating this.
It looks very exciting.
So Calvin asks, can MeerTrap dump raw voltage data to disk for offline localizations after incoherent beam detections?
That is an excellent question. So we do have a transient buffer mode, which we are in the process of testing. The problem is our false positive rate currently is not as low as we'd like it to be. So we do have the capability to dump voltages upon detection of a transient, and we've done so for sources that repeat. But once we have the false positive rates at a reasonable number, I think we'll be able to localize every Frb that we detect.
Okay, great. There's one more question from Daniele, but I'm going to ask you to just address that in the chat, if you will.
I'll do that.
Because I know that our next speaker, it's very late or early for her. Thank you again, Manisha.
Thank you.
So our next speaker is Shivani Bhandari, joining us from Australia. And Shivani is going to be talking about fast radio bursts with the Australian SKA Pathfinder. So take it away, Shivani, and I'll give you a reminder with 5 minutes left.
Thanks, Dunk, and thanks, Manisha, for setting the scene. I guess I can just directly jump in. Hi, everyone. I'm Shivani, and I'm currently a postdoctoral fellow at CSR of Astronomy and Space Science in Sydney. And I would like to thank the organizers for giving me an opportunity to talk to you today about fast radio burst with ASCAP. So as we know, to date, about 600 distinct FRB sources have been published, and out of which only 4% are observed to emit repeating burst. And while majority of the bursts are discovered by the CHIME telescope, the Australian Square Kilometre Pathfinder is currently leading the world in FRB localizations. To date, more than 40 bursts have been discovered by ASCAP, out of which 2 were seen to repeat. Few percent of these bursts have been localized, and I will talk more about them later in my presentation. Okay, to start off, ASCAP is a national facility located in the Murchison Radio Astronomy Observatory in Western Australia. The array composed of 36 12-meter dishes. The phased array feed technology facilitates the creation of 36 beams on the sky that can be arranged in different patterns, giving a 30 square degree field of view per each dish at 1.4 gigahertz. ASCAP can be operated in a frequency range of 700 megahertz to 1.8 gigahertz with an instantaneous bandwidth of about 300 megahertz and the maximum baseline of 6 kilometer, which gives a couple of arcsecond resolutions. We have been conducting searches for FRBs under the project called CRAFT, which stands for Commensal Real-Time ASCAP Fast Transient Survey. The block diagram in the left here presents the real-time FRB detection system implemented at ASCAP. The data is captured, it's reordered and incoherent slumped over all the antennas and all the beams in the data buffer, where a fast DM transform based GPU program called FREDA searches for single pulses and it records candidates. Now, Snoopy is another piece of software which listens to this real-time FREDA candidates and trigger the voltage term in case of an eligible FRB candidate. Now, the FRB report on the right here is also generated, which presents the discovery details and preliminary multi-beam localization, which is in initially 6 to 7 arc-minute accuracies. And after the trigger, the voltages are downloaded from the 3.1 second long ring buffer for offline interferometric analysis to determine the precise arc-second level position of the burst. So the real-time searches at ASCAP for FRBs in this particular interferometric mode were commenced in mid-2018, and we found our very first one-off FRB running in this mode on September 24th, 2018. So, and we were able to download the voltages and cross-correlate them offline, and we were very excited to work towards our first localization. Our efforts were successful and the burst was localized with a precision of 150 milliarc seconds, and optical observations revealed the host galaxy, which was at a redshift of about 0.32. And because of the precise localization, we can say that the burst came from the outskirts of a massive early type spiral galaxy, very different from the host of the first repeating FRB, which was a dwarf galaxy undergoing high star formation. So since the first discovery, the CRAFT survey at ASCAP has localized many more FRBs. So slide here represents the high resolution view of a sample of FRB host environments using 2 bands. So one is the ultraviolet band, which is shown in the blue, and the red is the infrared. And these are from the Hubble Space Telescope. And black ellipses are 2 sigma uncertainty on the position of the burst. Now we can see there that majority of the bursts are coming from the are offsets from their host galaxy centers, and the hosts themselves are a mix of spirals and more lenticular systems. We also found that FRBs are not in the region of elevated star formation in comparison to the mean global values in their hosts. So with this sample of localized FRBs, we conducted a study of the global properties of their host galaxies. In the left here, I show a plot of stellar masses of galaxies versus their star formation rates. We found that majority of FRBs to be massive galaxies and moderately making stars. We also found that the progenitors can arise from a very general stellar population, then exclusively from young stars. On the right here is the Bpt diagram, which uses nuclear emission line ratios derived from optical data to determine the dominant source of ionization in a galaxy. And it also kind of distinguishes between the star-forming galaxy, the liners, and the AGNs. As you see, FRB hosts have excess of N2 line, which suggests that they have high metallicity, and also majority of them are liner galaxies. And I should also point out that the host galaxy of 121102 remains atypical. So with these analyses, we also build on a sample to look at the host offset distributions and the global properties of the FRBs together. They both suggest that compact merger events, such as white dwarf mergers or neutron star mergers, and other processes like accretion-induced white dwarf collapse and core collapse supernovae, they all seem to be plausible mechanisms for the FRBs localized by ASCAP. Also, we found that the host galaxies hosting long GRBs and superluminous supernova, which usually happen in a faint star-forming galaxies, are less likely to be common hosts for these FRBs. So we also performed a search for supernova-like transients, optical counterparts for a sample of FRBs. So we obtained two sets of imaging epochs with the VLT for the three host galaxies. One was soon after the burst detection and other was several months later. And after subtracting these images, we did not find any optical counterparts associated with the host galaxy. Now the plot here on the left shows FRB host and their subtracted images. So with this analysis, we concluded that type 1a supernova or type 2n supernovas are unlikely to accompany every apparently non-repeating FRB. Right, so talking about counterparts, detection of an FRB in the commensal ASCAP craft observations also facilitated a search for radio afterglows before and after the FRB event. So FRB 191001 was the first ever FRB to be detected in such an observation with ASCAP. So during this observation, ASCAP hardware correlator was running and it was recording visibilities parallel to the craft system. And the FRB was so bright that it was detected in a single ASCAP 10-second snapshot. We searched for any radio emission from the position of the FRB during the whole 9 hours of observation, and we found no varying emission above the 5 sigma level. The peak here you see in the light curve is the actual FRB itself. So we conducted follow-up with Australian Telescope Compact Array, and we detected continuum radio emission, which was because of the ongoing star formation in the galaxy. So there was no radio persistent source associated with this burst. Now, since this burst, we have found 6 additional FRBs. So these are the pulse profile and spectra for some of our unpublished detections. As you can see, the DM of the burst vary between 300 to 730 parsec per centimeter cubic. And here is the slide presenting the host galaxies of these bursts. I request to please not tweet about these results just yet. So as you can see, the redshift of the hosts are 0.24 and 0.37 respectively. And we are still in the process of observing and analyzing the spectra for the host of FRB 210117. Okay, so some more FRB detections from ASCAP here. And I should note out that we were really excited to find the highest DM FRB in the ASCAP FRB sample. FRB 210407 was detected at a DM of about 1800 parsec per centimeter cubic. And we have only identified the host for FRB 210320, which is at a redshift of 0.28, and observation and analysis for other bursts are underway. Talking about repeating bursts now, very recently, CHIME reported the active nature of a repeating burst, and we conducted follow-up observations with ASCAP and found repeating FRBs from this source, which helped us to successfully localize the burst to a galaxy at a redshift of 0.097. We found the host galaxy to be typical star-forming, massive, and dusty. And also the galaxy was dominated by old stellar population, which has a mass weighted age of about 5 to 6 gigayears. Now this old stellar population suggests that the host can accommodate progenitors that have longer delay times. Additionally, we also found that the star formation rate of the galaxy was pretty much constant over the 10 gigayears history, with a notable absence of any star bursting nature. And finally, we found no evidence of a dominant AGN, and associating the persistence source, which was detected in observations from the VLA and GMRT. And we attributed this persistence source to the star formation that is happening in the galaxy. So now with an updated sample of 12 non-repeating FRBs and 6 repeating FRBs, we are currently analyzing the global properties of the FRB host population. So far, we are finding no significant differences in the hosts of repeating and non-repeating burst. So when comparing the FRB host with that of other transients, we find that the host of ultra-luminous X-ray sources and type 1a supernova to be much more massive and star-forming than FRB hosts. And scenarios such as long GRBs and superluminous supernova remain ruled out with this updated sample as well. And whereas the hosts of core collapse supernova and short GRBs are mostly found to be consistent with that of FRBs. Switching gears and moving to cosmology, the precise localization of FRBs with ASCAP has provided us the first example of DMZ measurements, which has resulted in a direct detection of the missing baryons in the ionized IgM. So the DMZ relation here is known as the McQuart relation. The gold sample of FRBs are overplotted, and this sample is observed to be consistent with the prediction of the lambda cosmology, which is shown here as black line. Now the gray zone here represents the 2 sigma scattered in the DM due to the intergalactic medium and foreground halos. So where the mean of this McQuart relation is telling us about the baryonic content of the universe, the scatter here sheds a light on its structure. Additionally, an opportunity to study the foreground halos presented itself. FRB 18, 11, 12 sightline passes at an impact distance of about 30 kiloparsec from a massive foreground galaxy, thereby probing its halo. So using the property of the FRB pulse itself, namely its rotation measure and the scattering, we concluded that the halo gas is diffused and non-magnetized. We have another case, similar case. So we have spectroscopically confirmed yet another foreground galaxy along the line of sight of another ASCAP FRB. Now the sightline in this case passes at an impact distance of 11 kiloparsec, piercing the halo of this foreground galaxy. The analysis is underway for signatures of halo gas in the FRB spectral, temporal, and polarimetric properties. Next, the closest nature for one of the FRB in ASCAP sample allowed us to study the high resolution environment of the host galaxy. Now here FRB 190608, which is shown in the right here, is localized to a spiral galaxy at a redshift of 0.1. The FRB is coincident with the knot of the star formation in one of the spiral arms, However, this is not the most active region in the galaxy itself. Again, by analyzing the RM and scattering of the pulse here, we concluded that the pulse broadening and Faraday rotation is likely to arise from the progenitor environment or the host galaxy than the IGM or the Milky Way. Also, another thing that we can do with FRBs is that the correlation of DM of FRBs with the distribution of foreground galaxy halos offers a unique way to disentangle the cosmic web. With this sightline for FRB 190608, we have performed an end-to-end study of the matter distribution using the spectroscopic and photometric data. We employed a slime model cosmic web reconstruction map to map the large-scale structures intercepted by the FRB sightline. Now, figure on the left here describes the 3D reconstruction of the cosmic web, while here on the figure in the right is the 2D representation of cosmic overdensities. Another such study is being performed in the sightline of FRB 180924. So this sightline is notable for its lower than average DM contribution due to the IGM. So we observed spectroscopic and photometric redshift of field galaxies within a region of 15 arc minutes of this sightline. The analyses reveal no foreground halo intersecting the line of sight closer than 100 kiloparsec. Thus, we conclude that this FRB sightline and most of the FRBs in general, their line of sights will have less contribution due to the IGM and halos as compared to the mean of the McQuart relation here. Okay, last but not the least is the high time resolution studies of our FRBs, which show temporal structures on timescales of tens of microseconds to few microseconds, while others are dominated by scattering. The polarization analysis here shows that the bursts are highly linearly polarized and have rotation measures of few tens to few hundreds radian per meter square. Also, we find the polarization, position angles, and the multiple narrow components to be ubiquitous for apparent non-repeaters. And a similar analysis is ongoing for some of the new FRBs in our sample. Finally, we are working towards upgrading the current craft system, which does the incoherent sum search for FRBs at the moment. The craft coherent upgrade, or CRACO, will enable full coherent search via fast imaging of visibilities. So this will make ASCAP 5 times more sensitive than the current method. So thus in the coming future, ASCAP will be delivering 0.5 to 2 FRBs per day with arc-second localizations. Speaking of future FRB localizations, Atmos telescope near Canberra is currently being upgraded to Atmos 2D. So this telescope consists of 1.5 kilometer long arms running east-west and north-south here. As a part of Atmos 2D project, 90 meter of the north-south arm is now equipped with these wider bandwidth and wider field of view cassettes. So the two square degree beam overlap here between the east-west and the north-south arm will allow the FRB localization with few arc-second precision. The installation of the new hardware is now complete, and a highly efficient multi-beam neural network classifier is being commissioned at the moment for real-time searching and triggering of voltages upon buffer. The plots here shows single pulses captured by north-south systems, which demonstrate that it's working. So yeah, so stay tuned for exciting FRB results from both ASCAP and Atmos. And I will leave you here with my summary and take questions. Thanks for your time.
Thank you very much, Shivani. Really appreciate the overview and all of these exciting new results that are in the hopper. I have a question from Daniele. He asks, the offset that ASCAP observes on the FRB positions with respect to galactic centers is usually only a few sigmas. That requires a good handle on both statistical and systematic uncertainties. Did you try localizing a good number of sources with well-known position to verify your localization capabilities?
Yeah, so initially when we were not finding any FRBs, we did test with on Vela pulsar, and we were able to localize it to its known position. So that was a reassurance that the system works. And as compared to finding the statistical and systematic uncertainties, we do observe calibration observations. So, and then there are a few sources in the field itself. So for doing the whole after calibration, we check the astrometry by comparing the position of those field sources, and we have pretty good confidence in our localization, because for the very first FRB we had an VLBI source in our luckily in our in the background field. So, and with the method, so comparing the position of the VLBI source with the position in our 3-second ASCAP image, we were pretty much in agreement, and that's how we built the confidence that this FRB was localized to 150 milliseconds.
Great, thank you very much. I think in the interest of time, we should probably move along, but feel free to drop any questions for Shivani in the chat. And really, again, thank you, Shivani, for jumping in the middle of the night. We really appreciate it.
Thanks, Dan.
Yeah. So our next speaker is Pragya Chola, and she is going to talk about the first CHIME FRB candidate. Catalog. Pragya, I'll hand it over to you.
Sure. You know, it varies.
Hello, everyone. I'm Pragya Chawla. I'm a PhD candidate at McGill University, working with the CHIME telescope to search and study fast radio bursts. Today, I'll be presenting the first catalog of bursts that has been recently released by the CHIME FRB collaboration, and discussing the constraints that associated studies have placed on the FRB population. So CHIME stands for the Canadian Hydrogen Intensity Mapping Experiment. It is a transit telescope located in British Columbia, Canada, and comprises of 4 cylinders, each 100 meters in length and 20 meters in diameter. Each of these cylinders is fitted with 256 dual polarization antennas, which are sensitive in the frequency range of 400 to 800 megahertz. The field of view of each of these antennas is 250 square degrees, extending 120 degrees in the north-south direction, since the cylinders are aligned along that direction. The field of view in the east-west direction ranges from 1.3 to 2.5 degrees, depending on the observing frequency. The inputs from these 1024 antennas are combined with appropriate phase delays to form 1024 beams on sky. These beams are searched in real time with a frequency resolution of 24 kilohertz and a time resolution of 1 millisecond. Since CHIME is a transit telescope, it only observes this strip of sky that is located straight overhead. However, as the Earth rotates throughout the course of the day, CHIME ends up observing the entire northern sky that is visible from the location of the telescope. Additionally, we have lower exposure for low declinations. The closer you get to the North Celestial Pole, which is shown here in red, the higher the exposure of the CHIME FRB system to that location is. Also, any locations with declination greater than 70 degrees are circumpolar to the CHIME telescope, and therefore we observe those locations twice a day in 2 transits, resulting in even higher exposure for these locations. CHIME operates 24/7, and this large exposure combined with the large field of view results in a detection rate of an average of 3 FRBs per day. This large detection rate has greatly changed the FRB detection landscape. So this is a histogram of the number of FRB detections as a function of frequency as of June 2018, so a month before the CHIME telescope came online. And at that time, the number of known FRBs was 60. Within the first year of CHIME operations, the number of known FRBs has increased to 600. And these FRBs include the 535 bursts, which were detected as part of the first CHIME FRB catalog. So the first catalog consists of 474 one-off FRBs and 61 bursts from 18 previously reported repeating sources. The dynamic spectra of 25 of these bursts is shown here on the right, with frequency on the y-axis and time on the x-axis, and the dispersive delay has been corrected for in all of these plots. The catalog includes several measured properties of the bursts, such as fluence, dispersion measure, width, scattering time scale, and the spectral parameters. Additionally, we provide localizations, which are computed based on the signal to noises with which a burst is detected in adjacent beams. This technique gives us localization regions that are of the order of 15 arc minutes. So the sky positions of these FRBs are shown here in the map in galactic coordinates. In blue are the non-repeating FRB sources, and the orange triangles show the repeating FRB sources. The background color map shows the exposure of the CHIME FRB system within its first year of operations to each of these sky locations. The exposure ranges from 0 hours to the locations that are not visible, to 50 hours at declinations close to 70 degrees. As I mentioned earlier, declinations greater than 70 degrees are observed twice a day. So we get two different transits, the upper transit and the lower transit. And FRBs close to the North Celestial Pole can get a maximum exposure of about 4,000 hours across the two transits. We can test this sky distribution for whether it is isotropic or not. This study was motivated by an observation with previous FRB surveys with the Parkes telescope, which suggested that the Frb rate is reduced closer to the galactic plane. We find that when we compare the exposure of the CHIME telescope as a function of galactic latitude, shown here by the dashed line, with the detections as a function of galactic latitude, shown here by the solid line, these two are consistent within error bars. This implies that we do not see any evidence for a reduced Frb rate at lower galactic latitudes. And we do these tests for FRBs detected above different sensitivity thresholds to account for any propagation effects that vary as a function of galactic latitude, such as scattering. Additionally, we can also correlate these sky positions with large-scale structure in the universe. This is done by cross-correlating the CHIME FRB catalog with 5 different galaxy catalogs. The angular power spectrum for the cross-correlation with one such catalog, the DESI-LRG catalog, is shown here on the right. On the y-axis is the significance of this cross-correlation, and on the x-axis are the different angular scales, with larger scales on the left and smaller scales on the right. These different curves represent the cross-correlation for different redshift ranges, and we find that we see maximum cross-correlation if we only consider galaxies in a redshift range of 0.3 to 0.5. This implies that CHIME FRBs inhabit the same dark matter halos as these galaxies. When we divide up the CHIME FRB catalog into different DM bins and perform a cross-correlation with these different DM bins, we find evidence for a subpopulation of FRBs that have large host DMs as high as 400 parsec per centimeter cube. Since we have a large sample of repeaters and non-repeaters, we can also perform studies to compare these two kinds of sources. So we see that repeaters exhibit complex morphology. This was observed for the first repeating FRB 121102, but has subsequently been observed in all of the repeater bursts in our sample. So on the right is one of the plots from a repeater showing these multiple peaks, as well as the downward drifting subburst structure, so the frequency for which reduces as time progresses. We compare a lot of properties between the repeaters and the non-repeaters, such as the dispersion measure, the scattering time scale, the fluence, and find no significant differences in the distributions for most of these properties. However, there are two properties, width and bandwidths, which seem to be different between repeaters and non-repeaters. So if you focus on the plot here, the repeaters are shown in orange and the non-repeaters are shown in green. And we find that the non-repeaters preferentially have lower widths than the repeaters, as well as higher bandwidths. Most of the non-repeating FRBs that we see have bandwidths close to 400 megahertz. That is our entire frequency range. For the repeaters, the widths are much larger, and the bandwidths are much smaller as well. So we have bandwidths ranging from about 50 megahertz to 400 megahertz. So while we detected these 500 FRBs, there are a lot of FRBs that we missed due to the observational biases that our real-time detection pipeline has. As an example, FRBs with higher DMs and higher scattering times are expected to be detected with lower sensitivity by our pipeline, primarily because of the effects of DM smearing and scatter broadening that would dilute the burst signal in time. So we account for all of these selection effects by evaluating a selection function. This is done by simulating 80,000 FRB signals and injecting them into the real-time detection pipeline to determine the probability with which a burst with any given properties would be detected by our pipeline. So the top plot here shows the selection function marginalized over the DM. As you can see, we have low sensitivity for FRBs at low DMs, close to 100 units, as well as FRBs at higher DMs, close to 3,000 units. And we can then correct the observed distribution for any FRB property based on our selection function to get the intrinsic distribution of that property. So on the left is the observed DM distribution from the CHIME FRB catalog. And on the right is this observed distribution, but corrected for the selection function. Once we have calibrated the selection function in terms of different burst properties, we can evaluate the Frb rate. So we evaluate the rate to be 800 FRBs per day above a fluence threshold of 5 Jansky milliseconds. The error bars on this rate are significant, and the dots here represent the MCMC sample showing the range that these parameters can take. Additionally, we also place constraints on the brightness distribution. So we specify the brightness distribution as the number of FRBs having a fluence greater than F, being proportional to F raised to the power alpha. The value of alpha is expected to be equal to -3/2 if FRBs originated from the local universe. Any deviation from this value would imply that there are some cosmological effects at play. In our case, we obtain a mean value of alpha of -1.4. However, the error bars suggest that this is consistent with the Euclidean expectation. This is something that we did expect to see because all of our FRBs are mostly at lower DMs, suggesting that their redshifts for a majority of our population would be less than 0.5, and we do not expect to see significant cosmological effects at those redshifts. Another interesting property of the CHIME FRB catalog is the scattering time distribution. So on the top is the selection function in terms of the scattering time. And while the selection function for the dispersion measure did not show more than a factor of 2 variation across different DMs, the selection function for the scattering time distribution shows significant variations. While we have really high sensitivity to bursts with low scattering time scales, any scattering time scales beyond 10 milliseconds are very hard to detect by the CHIME FRB system. So once we correct the the observed distribution of scattering time scales with this selection function, we find evidence for a large population of events with scattering times greater than 10 milliseconds, most of which are not detected by the CHIME FRB system. We interpret this population using a population synthesis framework, which simulates the intrinsic properties of FRBs, as well as scattering and dispersion measure, So to give a brief overview, scattering is when the sharp pulse from an FRB is exponentially broadened to result in the scattering tail. And it arises because of the fluctuations in electron density in the different intervening media that FRB signals propagate through. These media could be the host galaxy ISM or the local environment, any intervening galaxies that the line of sight to an FRB intersects, the intergalactic medium, or the ISM of the Milky Way. So this population synthesis framework simulates the properties of all of these different media and then tests different population models of FRBs based on whether they can reproduce the observed DM and scattering time distributions. So the host galaxy models that we are testing include spiral galaxies, dwarf galaxies, and elliptical galaxies. And we also consider different progenitors within spiral galaxies, such as magnetars, pulsars, and short GRBs. These progenitors vary in terms of their scale height above the galactic plane, as well as some of these progenitors are expected to show offsets from the galactic centers. So for example, for short GRBs, we would expect to see some offsets from the galactic center as compared to magnetars and pulsars, which are expected to be concentrated closer to the galactic plane. So the resulting DM and scattering distributions for these different population models are shown in the two plots here. As expected, dwarf and elliptical galaxies have lower DMs and scattering times. Dwarf galaxies because of their size, and elliptical galaxies because of the lack of free electron density. And amongst these different progenitor models that we consider, magnetars have the highest DMs and scattering time scales because of their lower scale heights, as most of the lines of sight to the FRBs, if they originate from magnetars, would pass closer to the galactic plane. So the first result that is coming out of this analysis is that if FRB scattering only originated in the host galaxy ISM, then we cannot reproduce the observed scattering distribution. This result is valid for all of the host galaxy types and the spatial distribution within the host that we test. So this inconsistency is shown here in the plot on the right. In blue is the selection corrected catalog, and in orange is the simulated distribution for magnetars and spiral galaxies. And as we see, we cannot reproduce the really high scattering time scales that we are seeing for a large fraction of the FRB population. So to match things better, we try and add additional sources of scattering. These include the circumburst medium. So the circumburst medium of the FRB is modeled based on the inferred scattering for the local environment of galactic pulsars. We also add scattering expected from the circumgalactic media of intervening galaxies based on a model proposed by Vedantam and Finney. While this model has not been confirmed by observations of individual FRBs, we find that we do need scattering from both of these sources in order to be able to explain the scattering distribution. Even after adding the scattering contribution of both of these sources, we find that the resulting distribution only becomes marginally consistent. So the plot here shows a short GRB-like spatial distribution in terms of its DM and its scattering time and how they compare to the catalog. While the distribution is consistent with an error bars, the significance levels are still low. So like adding these two additional sources of scattering can reproduce the resulting distributions, but only marginally. Additionally, if the circumgalactic medium is not a source of intense scattering, as is suggested by these models, then we can say that FRBs must inhabit more extreme environments than those of galactic pulsars to be able to explain the observed scattering distribution for the CHIME FRB population. So I leave you with a summary, and I'm happy to take any questions at this point.
Thank you, Pragya, for sticking perfectly to time. We have a question from Calvin, and he asks, have you considered adding intervening galactic disks or halos in addition to intervening galactic CGM?
So we haven't added those, and this was primarily motivated by results from Ocker et al. So this was a paper this year considering the scattering time scales of repeating FRBs for which we know the positions, and seeing whether we see any contribution from the scattering from these halos. And the contribution that is expected is orders of magnitude lower than the Milky Way. So we do not consider those contributions because they would not significantly impact our conclusions.
Thank you. I have a quick question about the DM distribution. How confident are you in, that plot there, for instance, or this one? You know, when you, with pulsar simulations, you know, as you get to, or any other population synthesis, when you have corrected samples with that are based on low numbers of sources, the error bars are really quite large. You know, how confident are you in the, you know, your abilities to predict the high DM range of the sample where, you know, really the sensitivity limit really kicks in?
Yeah, so we see that like the DM distribution really does not impact most of our studies. Like I agree that we are not that confident in the high DM range, but most of the models that we are ruling out are primarily being ruled out due to the lack of FRBs with higher scattering. So yes, if the distribution that we see for magnetars, like if we are missing the really highly scattered and the high DM events, then like these results, like we can still expect the host galaxy to be able to explain, to reproduce our observed scattering time distribution. But that would then be consistent with the results that we are saying that FRBs must inhibit more extreme environments than those we have seen for the so far like galactic pulsars that we've observed. So like these two conclusions should not be inconsistent in the sense that if we are missing those highly scattered high DM events from these simulations, then the result that FRBs must inhibit those kind of extreme environments should still be valid. And like most of these distributions, we are not rejecting them based on the DMs anyway. Most of the times the rejection comes from the fact that we cannot simulate the high scattering end of the distribution.
Great, thank you very much. So we're going to take a short break in the program right now. We're running a little bit behind. I suggest that we resume at what would it be, 17:45 rather than 17:40. So let's it's by my watch it's 11:37, so 37 past the hour. Let's resume at 1/4 to the hour, so 8 minutes from now. Okay, we're going to get started in a few seconds. Really enjoying all the presentations so far. We have 3 more invited speakers in this middle part of the session. And I'm going to ask Yuri when he's ready to share his slides. And then we can get underway.
Sure.
So it's a great pleasure to have Yuri speak today, and Yuri is going to be talking about fast radio burst detections and discoveries with Aptiv and LOFAR. So Yuri, please take it away.
That's right, Dunk. Thanks very much for having me. If you have trouble hearing me, just post something in the Slack and I'll try and adjust. Today I'm presenting our latest results of our Aptiv Frb surveys. I was looking at the names of the participants. I see there's a number of experts and a few people whose name I don't know so well, but all of you, you're very welcome to come visit Aptiv at Westerbork whenever you're in Europe at some point in the future. We'd love to show you what an amazing telescope this is. You can see it here on the right in this image. And on the right-hand side, you can also see on the sky how much the improvement of the field of view has been from the installation of the new Aperitif front ends. So you can see on the right, in the center of that field, there is the dashed circle. That's the old field of view of Westerbork. And in 2019, we installed new wide field receivers called Aperitif that increased this field of view by a factor 40. And they also doubled the bandwidth up to about 300 megahertz, somewhere in around 1.4 gigahertz. It's an east-west array of maximum length 3 kilometers. For FRB research, we usually don't use the longest baselines, but I'll talk about that in a bit. Of course, a big team of people were involved in building it. And so I'm presenting this on behalf of the Alert and Arts and Aperitif teams. Last summer, we made this flyover. It's actually been a while since I've been there myself, but it's still a pretty amazing instrument. Built in the 70s, 25-meter dishes, 14 of them. In 12 of these, Aperitif has now been installed, and you can see they're equidistant. Most of them are equidistant. And that's you'll see later that that's a huge benefit for getting coherent sensitivity over the full field of view. So Aperitif is a survey instrument. We run 3 surveys. 2 are for imaging, and so they do 1-second integrations of a field, like in this case 33. But occasionally, if you would turn up Aperitif and make it turn it into a high-speed camera, like we did for the FRB survey, then as you see here, sometimes some of these millisecond frames have a bright pixel in them. And of course, I think many of you know that if you really look at this bright pixel, it doesn't all stick to one frame. The different colors, the different frequencies arrive at different times, like pulsars do. And so here on the left, you can see a plot like that. With 1300 megahertz at the bottom, 1500 at the top, and a pulsar on the left-hand side with the dispersion measure 200. And this fraction of the Milky Way electron content that you see listed there of 0.02, 0.12, it tells you, this source encountered 12% of the electrons that are modeled in our Milky Way. But on the right-hand side is an amazing FRB from a few years ago that rates that goes up to 30 times the number of electrons that we can expect in our Milky Way, and so that was a big deal, and it still is. Sometimes I think we work on FRBs every day and they kind of become normal, but really they're not that normal. So I made this plot again some time ago. It's just before the CHAMP catalog came out, where you can see in the bottom panel the pulse width of pulsars, regular pulsars, giant pulse emitting pulsars, but some magnetars too, compared to their bandwidths, compared to FRBs, one-offs and repeaters. And you can see that in the bottom plane of this field, they are pretty similar, but on the z-axis, the order of magnitude change in luminosity, 10 orders of magnitude, is just amazing. Continues to amaze me. And so that's why we try and find more of them and understand them better. Personally, I'm mostly driven by understanding FRBs themselves better, but of course you can also, like we do with pulsars, apply them for other parts of science. And so for measuring baryon densities in our universe or other kinds of cosmology, they're very interesting. Personally, I like a lot the plasma physics and the particle acceleration side that perhaps this FRB emission mechanism requires. So it's pretty hard, as many of you know, to build a system like that. And we were pretty proud to be one of the first to do this on Aperitif. We built ARTS. It is a hybrid real-time supercomputer based on many stages of FPGA beamforming to combine all the dishes, first the front ends, then the back ends. It's all customizable. I'm not going to go into it, but we found a good setup that we use most of the time now. And then it rounds all this data, more data than the whole internet of the whole country of the Netherlands that this telescope's located in, through a big GPU cluster that you can see a picture of on the right here. As in many places, if you're in the desert or if you're in a country like the Netherlands, there's lots of GPS satellites. And so RFI is all over, and the real-time RFI accession has been very important. Also, the folks from the Netherlands eScience Center, you can see the logos at the bottom, were very helpful in building the real-time search software, Amber. It's all open, please use it. It has powered all our discovery so far. So what does it do? You can see here, if you look at the top right, you can actually see the dipper of the Big Dipper in there, in those 4 stars, and the 5th just above the A. That gives you a feel for the 10 square degree field of view that Aperitif produces. And within these, we have a bunch of compound beams. That's the 40 gray circles. And within these, again, we produce all the tide array beams. Those are the coherent beams. Now, like I was saying, aperitif is an east-west array, and this means that we have very good localization in east-west direction, but we have no baselines in north-south direction. So in the north-south direction, our localization isn't that good. A single beam measures about 25 arc seconds by half a degree, which is interesting. I'll talk about that later, but of course it's extra interesting if a source repeats, because the beams rotate on the sky, and then in the bottom right, you can see if you were to detect a repeater at 2 different hour angles, then suddenly you're back to a few arc seconds. It depends on the signal to noise, of course. And that's what we've been doing. It runs all the time. Like we saw on Meerkat, it was a commensal system there. We do a lot of dedicated pointing, but it runs all the time. And like we've also been hearing, the amount of false positives is sometimes pretty challenging, same for us. But it does mean that you need to be smart about weeding down the number of candidates that you need to look at in real time. And so that's why Liam, Connor, and I produced this neural net to recognize the FRB features in real time. Beforehand, of course, we would all do this by eye. But after our last similar LOFAR project, we had to look at 120,000 candidates by eye. That was really the limit. And so now I'm glad that we implemented this, because this has really helped a lot. And it runs very quickly. It runs within a minute of real time. And so within a minute, we know if what the probability was of the whole detection throughout the entire system. And that'll become important later. So what do we do in Alert? Alert is the name of the FRB survey that we're on aperitif. If we assume our dishes can point, so we have a couple of good benefits. We don't have to wait for the sky to pass over. We can target interesting fields, and we can target them for longer than, for example, Chime can. So if Chime finds a repeater, then we could put some more time on it if that's useful. If you combine that with the idea that FRBs happen all over the sky, and really there's not a great deal of benefit in tiling out the entire sky, which was our original plan, then our field priorities are now like this. They're based on our motto to first detect, later localize, and finally characterize, but we can do this with other telescopes detections as well. So what we do is we target fields in which we know that candidates exist, preferably ones, repeaters perhaps, that need to be localized better. Because if we get 2, like I was saying, we could provide good localization. And within these fields, you get new detections anyway, like you did in blank fields. If there are repeater FRBs that are already localized, but they could benefit from a further characterization by putting more time on them, then we do this too, and we get our new detections with those as well. And then finally, if there's nothing up, then we take blank fields. We actually detect about 90% of our new FRBs in fields of existing FRBs. It's because we put the time in there, but that's where we find it. Imaging takes 4 weeks, and then we take a week with the FRB survey, and we're running until the end of this year. It's a little bit sad. I would have preferred to continue these surveys, but the end of 2021 is the end of the operations of the aperitif surveys, imaging and FRB, as they are currently standing. So we were very excited. It's 2 years ago now that we found our first FRB, FRB 190709. After a lot of prep, of course, I was very happy to see the system work. It's an FRB that's roughly at the 50th percentile of the known flux distribution, so it's pretty spot on. And it was a very exciting moment to get that started. Here you can see two interesting plots that Liam Ostrom made for his thesis. On the left-hand side, in the 2 plots, you can actually see the chromatic effect of these wideband receivers. You can see that the main beam, where the light appears white, is where we see the FRB of the full band. If you go further out, then the chromaticity of the beam response becomes more and more apparent. And so that makes it pretty obvious what the real location is. And that's the ellipse you can see on the right. So far, we've found about 24 one-off FRBs. We get about 1 every 5 days of observing. I think we got to redo these numbers after seeing a few of these talks, but I think that makes us one of the most productive L-band servers in the world. And what's neat is, of course, that it's not just about rates. It also means that with the the error ellipses that we measure, we get interferometric, we get good interferometric localization with an accuracy that really allows you to say something about the line of sight. And I'll show an example in the next few slides. The distribution of our one-off FRBs is actually, most of them are quite high DM, and we see quite little scattering, and they're very narrow. We see more than in CHIME, a number of FRBs with multiple components, and they're all quite broadband. And it's not just the training of the machine learning algorithm, because we've retrained it in different ways too, but we've hardly seen any that don't cover the full band. So that's interesting. Overall, of course, these findings, they follow from our instrument strengths, and that's that we have high time and frequency resolution. So here's an example of what this interferometric localization can do. 1911-08, we localized it to an ellipse of about 5 arc seconds by 7 arc minutes, always east-west versus north-south, basically. And the neat thing is that it cuts really close through the halo of M33, and so also of M31, because that has a very large halo too. We just heard, of course, the interesting result from ASCAP sources where FRBs cut through halos. So we were very excited here because it cuts within 18 kiloparsecs of M33. What's neat though is that in contrast to the source that was mentioned earlier, here we find very little evidence that the halo added almost anything. The rotation measure is quite high, about 500 units or so, and it must all come from the host vicinity. So as we've seen in repeaters, for this FRB at least, there must be a pretty intense magnetoionic environment around the emitter. Like I was saying earlier, we find many of our one-off FRBs in repeat fields, and you can see the same here because, of course, after we discovered 1907-09 for the first time, it became one of our go-to fields, and we found 2 more FRBs that cut very close through the halo of M33. So that is even giving us 3 sightlines that cut through at different distances. What's neat in a system like this is you can also do imaging. Here is the imaging of the field. If this source would have had a persistent source like 121102, then we would have seen it, but we didn't see it, so it must be further out. I'm going to skip this slide in view of time. And move from one-offs more to repeaters. The 3-hour tracks on repeaters mean that Aperitif can help a lot with improving localization, especially like I was saying, when you get different hour angles. And you can see here at the bottom an example where there's 3 individual bursts of a known repeater combined. And on the right-hand side, you can see the final field. It's about 10 by 10 arc seconds. And our localization agrees very well. It's hard to see, but with the little cyan X that marks the known location. And so we've done this on a number of sources, but our main candidate has been target of a campaign together with LOFAR. So here you can see Westerbork on the left. The sky is actually the continuum sky. I don't know if you can see it with the resolution. Combined continuum sky with Aperitif and LOFAR, so you can see some very nice galaxies with long tidal tails and double doubles. On the left-hand side, Westerbork, HBAs from LOFAR on the right-hand side, and a little mist in the background, which is, of course, why I like this plot a lot, because many of us have tried for a long time to find FRBs with LOFAR. LOFAR is great for pulsar, so why shouldn't it be able to see FRBs? If we know with Westerbork that sources repeat at the high frequencies, the blue, if you will, then is there any red? Or is it all stopped by a dense electron mist, like this mist we see in the picture, but then around the host? That's, of course, what we were keen to find out. And we tried this on one of the most frequent repeaters, 1809-16B, at Aperitif and LOFAR. And you can see here on the right that the FRB comes in very brightly at the Aperitif side. The real-time system finds it. And we both trigger LOFAR and look at the data that we were recording. Nothing there. So that was a bit of a bummer. And so maybe the mists were stopping low-frequency emission after all. So for 2 days, Aperitif bursts came in, but nothing was seen on the LOFAR side. But then when the Aperitif burst stopped, you can see this on the top right, the LOFAR burst started. And then 3 days worth of LOFAR bursts appeared. So they were never seen at the same time. Well, that's pretty interesting because if repeater FRBs are produced by binary wind systems with eclipses, then it should really be the other way around. The blue should be long, well, they should be happening at the same time, but also the blue should be emitting longer. And here, sorry, I say blue, high frequency apparative data should be emitting longer. But what we see is the low frequency radio, LOFAR data coming in for a longer time. This was very exciting, of course, because I had never seen an FRB with LOFAR before. And so we were very glad when these pictures came up. It was really exciting. And it shows not only, like I was saying, that there's some interesting results for binary systems, it also just shows that FRBs are visible at these low frequencies. And that's a really big deal because it does mean the radio emission can get out. It does mean that there must be a clean environment around this fast radio. I was mentioning this earlier already, but here you can see it in a plot. A very similar trend was seen even with more LOFAR bursts in Ziggy Pleunis's paper. But we show here that apparative data arrives before the LOFAR data and is more narrow. We conclude from that it's not a simple binary range. Of course, there's other FRB models like isolated magnetars. They could be fast spinning, they could be slow spinning. They all have issues. I'm not saying they're perfect, but an isolated magnetar with a synchrotron laser shock emission model, it works for the data that we get. What's surprising is, and then I'll wrap up, that the source is actually more active in our campaign in LOFAR than it is at apparative for the same frequency. And if you want to look up the paper, I have the archive link at the bottom. So that's it. Aperative's been pretty successful so far in FRB every 5 days. Good one-offs, good rates, good localization, and now also simultaneous detections with LOFAR that have led us to a number of interesting results about the FRB emission source mechanism. And that's it. Thank you.
Thank you very much, Yuri. Really nice results. There's a little bit of time for questions. People want to drop them in the chat. I have a quick question for you. You presented those results in terms of the phase of the repeaters. How well can you actually measure the phase? I mean, is the period that well known that you can?
Yeah. I posted the archive link there, so people who are really keen can go dig this up. But we did do an extensive analysis on all the bursts that we took, the public ones from CHIME and the ones from LOFAR, to see if there was, because I presented here as a phase, so it's a 16 phase, but not all these bursts occur in the same cycle. And so, of course, if you get the period wrong, then you're going to get this window wrong. And so we really did a very thorough analysis of what the range of potential periods could be. And it's basically the same period as was already previously concluded from the CHIME data. So we're very confident that this phasing is correct.
Okay. Thank you. If anyone else has a question, please speak now or forever hold your peace. Just unmute yourself if you'd like. All right, if not, thank you, Yuri, again. And let's move on to our next speaker. And that is Anastasia Fialkov. Anastasia, please go ahead and share your screen. Welcome. Your title of your talk today is Cosmology with High Redshift FRBs. So when you're ready, please go ahead.
Thank you, Dank. And I figure that there are not too many cosmologists in the audience, so I'll give a bit of introduction and talk about what can we learn with high redshift FRBs. So we all know that cosmology has advanced in the last few decades tremendously, and a large part of this evolution was due to the observations of the cosmic microwave background by a series of instruments starting from COBE in 1992, and the most recent results from Planck show primordial spectrum of fluctuations in matter through how they look in temperature density fields. And from these observations, we can constrain our cosmology based on, for example, lambda CDM theory with only 6 basic parameters, to conclude that dark matter forms a large part of overall matter density in the universe, around 26.8%. Baryons compose only around 5%, and the majority of it is dark energy. CMB is also sensitive to ionization, the last phase transition when neutral gas filling the space between star-forming regions was ionized by stars and galaxies. And CMB observations roughly place redshift of ionization to be at 7.5. So very early on in the first billion years. And they measure optical depth to a precision of about 10%. Of course, the CMB probes only two-dimensional surveys in the history of the universe and ionization, to which it is very weakly sensitive. And it's just one picture of the universe. And of course, the universe underwent through a lot of evolution between the CMB and the present day, with the formation of first stars and galaxies, which heated and ionized the intergalactic medium, and the formation of more massive galaxies clusters that fill the space today. So there are a lot of observations of the local universe, in particular recent DES Dark Energy Survey released 300 millions of galaxy spectra, and they probe cosmological parameters today to great precision. Based on that, we know that the universe accelerates. There are tests of general relativity on multiple scales, and we can inform galaxy formation theories to high precision, so that simulations can actually mimic very well formation of the Milky Way. Unfortunately, observations of the epoch of ionization and also formation of the very first stars and galaxies are still very vague. There are very few observations of bright quasars, because bright quasars simply don't exist at early times, and also galaxies that can be directly observed are very rare. So the bulk of the universe between the CMB and the end of the epoch of ionization remains virtually unobserved. So for example, this is on the bottom right here, I show the redshifts of observed quasars, and we see that they basically are extremely rare at redshifts above 6.77, and there might be only one quasar at redshifts above 7 or 8. And also each quasar has a very weak, imply very weak constraints on the ionization history through the absorption in the wings of the quasar spectrum. For example, on the bottom left, we see the PDFs of the neutral fraction constraints from individual quasars at high redshifts, and they're very broad. Anywhere between ionization fraction of 0 and 1 is still plausible, basically, based on these quasars. As I mentioned, CMB is very weakly sensitive to ionization, and uncertainty in the optical depth to ionization is around 6 to 10% from the CMB, which deteriorates constraints on all the other cosmological parameters, because tau is degenerate with the amplitude of the initial fluctuations in the matter density fields. One of the most promising probes of this field is actually 21 centimeter line of neutral hydrogen, but at the moment there are no observations except for one tentative detection that is still not verified, and there are multiple upper limits, but constraints on ionization are still weak from that point of view. In addition to ionization, there are many other open questions in cosmology, like of course, nature of dark matter. We have no idea if it's cold or maybe warm, or if they're ultralight axions that are, for example, supported by string theory. We don't know the nature of dark energy, and there is tension in the measurement of H0. Our galaxy formation theory is still not super pinpointed, and the structure and composition of IgM is not very well studied. And as I mentioned before, we don't have any observations of the first billion years of the formation of first stars and galaxies. So my personal hope is that FRB will provide a way to probe this epoch of ionization and formation of first stars and galaxies in a unique way. They are complementary to both CMB and galaxies, and they therefore can probe it in along new lines. It's interesting that already existing telescopes such as FAST and GBT could be sensitive to high redshift FRBs out of to redshift 10. And of course, SK should be sensitive to FRBs all the way to cosmic dawn if they're as bright as today. So we already have seen there is quite a body of work accumulated that low redshift FRBs are very useful for cosmology to constrain the missing baryon fraction and to measure H0 and to measure omega m and baryon content in the intergalactic medium. And it's very interesting to think about what can we learn with high redshift FRBs. We did a small study with Avi Loeb several years ago to just estimate out to which redshifts telescopes such as SK can observe them based on the luminosity of FRBs known at the time. And the brightest FRBs can actually be observed all the way to redshift 20 if they exist there. So in principle, we can probe the epoch of ionization and formation of the very first stars. So some basics, of course, FRBs are dispersed, as we already heard from very nice talks earlier today. And this dispersion is proportional to the column of the ionized gas. Therefore, if we are placing FRBs into the epoch of ionization when the universe was still partially neutral, the dispersion measure would saturate for high redshift FRBs. So we would expect to measure the same dispersion measures at a range of redshifts deep into the epoch of ionization. So before it actually started. And then as the ionization gets on the way and progresses, the dispersion measure would decline accordingly to the electron density. There is actually a one-to-one correspondence between the observed dispersion measure and the optical depth out of which to that redshift. And therefore, a dispersion measure of an ensemble of FRBs can be used to probe the CMB optical depth. And again, making a very simple estimate with Avi, we found that if you know dispersion measure out to with a precision of 100 in the standard units, then it would give an uncertainty in tau of about 0.3%, which is of course much higher than Planck. So I was interested what actually, going beyond this very crude estimate, what can we do with a realistic ensemble of FRB measurements, assuming they exist at high redshifts, and asked my student Stefan Hammersheim, who is in the audience, to do this calculation. So Stefan looked into, he created a realistic catalog of fast high redshift FRBs, assuming that they scale with, the abundance scales with star formation rate, and explored how changing different cosmological parameters would affect this dispersion measure. So simply put, if you change omega b, the ratio between omega b and H0, it simply changes the normalization, and DM would, the saturated level would go up or down. And this is degenerate with the effect of omega m on the dispersion measure. But ionization parameters such as midpoint and duration of ionization have a non-degenerate effect on the dispersion measure. So the hope is that you indeed can measure ionization to high precision using such a catalog. One point that we wanted to be careful about is using models, because assuming a model that is actually not realistic can lead to biases in the end results. For example, again, Stefan found that using Tanch function, which is usually used in the CMB to model ionization, would lead to about 10% underestimate in tau if the reality would be different. So even assuming realistic models, but based on simulation, could lead to such biases. So we wanted to come up with some model-independent parameterization for our study. We adopted a method called FlexNode, which is already used in, or was invented for CMB cosmology. And in this case, ionization history is parameterized by a series of knots instead of assuming a specific shape. And these knots are positioned in both redshift and ionization fraction, and their position can vary. We also explored how many knots are needed to actually parameterize ionization history. And then this method was used to actually simulate ionization instead of assuming a model for it, and extract limits on cosmological parameters. So we looked at two different catalogs of 100 and 1,000 Frbs located between redshifts 5 and 15 and distributed according to star formation rate, which seems to be supported by low redshift observations. And just to give you an example, in this case, about 85% of Frbs are at low redshifts between 5 and 8, and only 3% are at very high redshift and between 10 and 15. And we took all possible errors into account, so I will skip these details. So these are the final results that Stefan obtained. And in green here, you see the input, actually a fiducial model that was used to generate catalog. And then in orange are the posterior distribution of the ionization history extracted using this FlexNode algorithm based on 1,000 Frbs. So we also added, because there are only 3% of Frbs above redshift 10, we looked at what does it make to add, what effect would it be to add constraints from the CMB on the high end of the ionization history. These are constraints from CMB polarization, and they actually help to improve constraints on the tail at high redshifts. So using both 1,000 Frbs with localizations, where we assumed the photometric measurement of the host galaxy redshift and CMB constraints, results in a pretty tight constraint on ionization history, especially at low redshifts where there is more data on Frbs. So we looked at what actually the resultant constraints on tau, which is the most interesting information one can obtain from a high redshift Frb population, in my view. And we found that there are about 100 Frbs are enough to have compatible constraints to Planck. And going beyond that will allow us to shrink measurements of tau. So now this is very important because better precision in tau would allow us to improve constraints on all the rest of cosmological parameters, specifically on the amplitude of the primordial spectrum fluctuations. And in turn, it would improve constraints on neutrino masses, for example. Other parameters we found, such as omega m and h naught, are better constrained with low redshift Frbs, and also because the observations there are easier and there are more Frbs and with localizations. Another interesting aspect to look into regarding high redshift Frbs is their possible constraints on star formation at high redshift and galaxy formation and the physics of ionization itself. I found this paper recently very interesting, where they constrain parameters of ionization, such as ionizing efficiency of sources, or typical mass of star-forming halos, or bubble size of ionization, based on the, again, distribution of dispersion measures extracted from a simulation. So in this case, Frbs could tell us about the nature of ionizing sources and how topology of ionization was actually, what was the topology of ionization. Another interesting field of study that we are exploring in my group is actually what could we expect from a population 3, from population 3 stars in regard with Frbs, assuming that formation mechanisms are similar to what we have today. Of course, this doesn't have to be the case, but if there are similar systems and they produce Frbs, then we could expect to observe them from population 3 stars. And we find that varying properties of population 3 stars, for example, their initial mass function, could strongly affect number of Frbs expected in different Frb progenitor theories. For example, if Frbs are produced by systems by binary systems where two components are white dwarfs, then we do not expect such Frbs from high redshifts if primordial initial mass function is top heavy, just because there are no light systems there that produce white dwarfs. While we can expect to have Frbs from black hole mergers. I'm not sure if I'm on time, but here are my summary. So I think high redshift Frbs would be extremely interesting constraints of ionization history and optical depth. They will help to constrain further primordial spectrum of fluctuations and help constrain neutrino masses. However, they will not add anything new or much new information for constraints on matter density and H0, because just low redshift Frbs are more abundant and easier to measure. And I think high redshift Frbs could be potentially interesting probes of astrophysics at high redshifts and population 3 star formation. Thank you.
Thank you very much, Anastasia. There's one question came in from Calvin asking about the DM measurement requirements and whether a redshift was needed. But Stefan, I think, has already answered that, saying that you assume a 10% redshift measurement.
Thank you, Stefan.
So does anybody else have anything to ask? Now would be a good time to do so. If not, I'm going to...
I have a question.
Go ahead, Zorba.
So what about the theory of AGN feedback and forming the first galaxies? Could Frbs help with that?
I think that would be, I'm not sure what you mean exactly, but to me it sounds like it will be degenerate with other processes. I would need to think about it more, to answer it better.
Okay.
Okay. Well, thank you again, Anastasia, for that nice overview and some really exciting results. Vicky, do you have something to...
Yeah, just a quick question. So we'll hear later a talk by Jane about outriggers for CHIME and the possibility of localizing 1,000 Frbs, but not at the redshifts that you would want to measure that saturation. And I guess what I'm wondering is, let's say you don't quite reach the saturation, but you measure that's well, how many do you need? I guess you could simulate, like, what is the minimum that would be interesting to start to see a turnover that would be informative. That's what I'm wondering.
We can definitely do this calculation. And Stefan, if you can participate. All right, we don't have time, but I'm happy to do this, explore this further.
Okay, thanks.
Great. Thanks again. We're going to move on to our last invited talk today. Yuri Lyabarsky is going to be telling us about FRB emission mechanisms. And Yuri, take it away.
Hello, everybody. I have a difficult task to overview emission mechanism of FRBs for a bit more than a quarter of an hour. I try to touch upon only basic physics without any details, and hopefully it would be understandable. So we definitely deal with coherent emission mechanism, which means that many particles emit in phase. How many we could estimate from the observed brightness temperature? This number is huge. It depends on the Lorentz factor of the source if it moves towards us, and also on the energy of particles, which could be relativistic. Okay. In any case, this number is very high, and this minimal number. And it's natural to look for a mechanism in plasma, because in plasma, due to long-range interaction, coherent motion of large ensembles of particles could be excited relatively easily. One has to just take into account that the same long-range interaction strongly affects both emission and propagation of radio waves. Therefore, there are three basic questions any model has to answer. First of all, what electromagnetic waves could propagate in plasma at given conditions? The second, how could these waves be excited to the observed power? And last but not least, how could these waves escape as radio waves? If could, of course. The straightforward idea that there are bunches. So many particles move together and radiate as a single entity, which is okay. And the question is how these bunches could be formed first, and the second, how could they radiate? By some historical and maybe psychological reasons, the most popular model is still the model of curvature emission of such bunches. Because it seems to be very simple. If bunch moves in neutron star magnetosphere with Lorentz factor about 100, it emits in radio band, which is okay. The origin of these bunches is difficult questions. People refer to stream instability, which could produce fluctuation of charge, but with energy not larger than the energy of the plasma. The problem is that if we know number of particles required in bunch, we could estimate the repulsive electric potential in this such a bunch, and we see that it vastly exceeds the energy of particles, unless plasma is extremely relativistically hot. In all models of this sort, people consider two-stream instability in cold plasma, which drastically differs from hot. And in any case, even presence of the plasma that hot in magnetosphere is problematic because of very short cooling time. It seems that nobody even considered these problems, and therefore, till now, there are assumptions that such bunches are formed, necessary bunches. Looks quite arbitrary and not grounded. Another problem is the radiation, because this plasma is very dense. Again, we know how many particles we need, and we know the volume. At this density, the shielding scale, plasma shields charges. This is the basic property of plasma. Shielding scale in this plasma is many orders of magnitude smaller than the wavelength of emitted radiation, which means that any emission is highly suppressed, which could be straightforwardly calculated. This is power of emission from point charge, curvature emission from point charge in plasma. And you see that as compared with the vacuum case, we have also suppressing factor, which is of the order of 10 orders of magnitude and so at these parameters. Again, all this ignored, and people use just formulas from Jackson's textbook. And by all these reasons, I think that this sort of model could not be considered as physically consistent, and therefore I would prefer not to discuss it in more details. Let us go to something better compatible with basic physics, and then we go to masers. Basic picture is well known. This is from Wikipedia. If in quantum system upper level is overpopulated due to induced emission, initial radiation is amplified. This is correct. But we deal with classical system, of course. Therefore, all processes we are interested in should be described without quantum mechanism. Classically, maser is a resonantly unstable medium, such that a seed wave satisfying resonant condition modulates this medium, producing charges and currents which radiate in phase with initial wave. In this case, we could also say that there are bunches of particles which radiate, and this is correct. But in this approach, both formation of bunches and their radiation are considered self-consistent, and therefore one could trust to these models. Specifically, when we deal with Frbs, people discuss synchrotron laser, which is simply a ring of electrons rotating in magnetic field. Evidently, in this case, we have a reverse population. There are no electrons with smaller energy. Classically, this system is unstable with respect to modulation. So initially homogeneous ring is modulated, bunches are produced, they rotate, and they emit synchrotron emission. Two important points. This works efficiently only if electrons are relativistic. And the second, as distinct from spontaneous synchrotron emission, which is dominated by very high harmonics of rotational frequency. Maser works at not too high harmonics. Depends on magnetization of the system. Magnetization is the ratio of the magnetic to the plasma energy. If magnetization is large, maser emits at basic harmonics at first harmonics. At small magnetization, higher harmonics, but typically not too high. In any case, this frequency is above the plasma frequency, which is good. The question is how to produce such a non-trivial particle distribution. The answer is at a shock front. This is a very old idea. When plasma enters shock front, it stops and particles begin to rotate in the enhanced magnetic field. This idea was confirmed by many simulations, by many groups. Indeed, people see this is shock, this is upstream flow, this is density, and density jump. And here are fields. We see upstream, strong fluctuations. This is radiation. According to simulations, about radiation, which is more than enough for Frbs. In terms of bunches, it could be also described in terms of bunches because we could calculate the charge of these bunches. And then we see that the necessary excess of plasma density is comfortably smaller than the average plasma density. And repulsive potential is smaller than the particle energy. So nothing extraordinary. And therefore, mechanism is robust. And one could rely on it. Radiation is linearly polarized, perpendicular to the magnetic field, but could not reach 100%, which is important for us Frbs, because sometimes we see high polarization. Shocks could be observed at many relativistic shocks at many astrophysical environments. I discuss magnetar flares in a couple of minutes, but before I would like to describe one more mechanism, less widely known. I mean, radiation from reconnecting current sheet. Current sheets separate oppositely directed magnetic fields. Such current sheets are unstable with respect to splitting into linear currents. Here is three-dimensional picture. You see these linear currents. In cross-section, they look like islands. Therefore, people sometimes talk about magnetic islands. Here are these islands, but each island is in fact current flowing into the plane of the picture. Islands grow, merge, and so on. linear current varying in time is antenna. What is antenna? It's just a linear conductor with variable current. Therefore, this is true antenna mechanism. On the other hand, this analogy was not very useful because antenna radiates in vacuum, whereas here all frequencies are small as compared with the characteristic plasma frequencies. And therefore, the system is, in fact, MHD system. As MHD interaction. Namely, when these currents merge, parallel currents are attracted. Therefore, these currents continuously merge, are produced and merge and again and again. When two islands merge, they disturb magnetic field around the merging point. And this disturbance is propagated away as MHD wave. This is seen quite well in simulations. Here are simulations of current sheet here. Color here is Poynting flux. Blue is to the left, red is to the right. And you see spherical, cylindrical, in fact, pulses propagated away from merging events. All the time, 1% of the dissipated magnetic energy goes to these pulses. Width of these pulses, which determines wavelength, is about the size of these islands, which scale with the alarm radius. So everything could be estimated if you know parameters of the system. Again, these waves are MHD waves, in fact, magnetosonic waves, which resemble sound wave, but with pressure, instead of plasma pressure, here is magnetic pressure. Plasma oscillates along in the direction of propagation of the wave. Magnetic field also oscillates. But, so this wave is longitudinal, but as electromagnetic, it is transverse because there is electric field perpendicular to the motion of particles and the background magnetic field. When plasma is magnetically dominated, so the magnetization is very large. This wave smoothly converted into normal electromagnetic wave because speed of this wave goes to the speed of light, electric conductivity current goes to zero, and we get normal electromagnetic wave. And what is important, 100% polarized perpendicularly to the background magnetic field. This is very non-trivial situation to produce. To produce completely polarized radiation, and this mechanism does produce. Again, reconnection could be seen in many objects. 2 minutes about magnetar flares. Important point is that in the course of magnetar flare, magnetic field is restructured in the inner magnetosphere and produces magnetic pulse, which propagates away. It is relativistic, it transfers energy away. If it produces shock, it could produce Frb. If reconnection happens within this magnetic pulse, it also could produce MHD, Frb. Magnetic field in this pulse exceeds the background magnetic field in the magnetar wind. There are different possibilities for formation of shocks. I couldn't discuss, I have no time. Maybe the best developed idea is the shock is formed in the wind itself. If the wind is heavily loaded by plasma, so it is moderately magnetized and only not highly relativistic. In this case, one could get Frb in the gigahertz range, at very wide range of luminosities of Frb, which is compatible with observation. The problem of this model is polarization. Could never reach 100%. And the second position angle in this model is determined by the field in the magnetar wind, which means that the position angle is fixed. It is polarization is in direction of the rotational axis of magnetar. But in some cases, we see a variable position angle. Frb from reconnection, we need current sheet. We have current sheet in magnetar wind, like in pulsar wind. Therefore, in principle, if this pulse from the flare enters the wind at the light cylinder, it compresses the current sheet and triggers violent reconnection, and this produces Frb. One can estimate that one could get reasonable luminosity of Frb at reasonable frequency for stronger Frbs. But in this case, because because everything occurs at the fixed distance. Frequency strongly depends on the luminosity. Therefore, weak Frbs is at too low frequency. Presumably, one could find reconnection site not considered yet. The advantage of this model, it could easily produce 100% polarization, and position angle in this case is determined both by the magnetic field in the wind and by the magnetic field in the pulse, which is variable, and therefore one could explain diverse polarization pattern. Okay, I have no time to discuss propagation effects. Therefore, conclusion for a while, we have two workable models of Frb. With both of them have the pros and cons. Of course, everything is based for a while on preliminary considerations and preliminary estimates. More simulations, first of all, simulations are necessary in order to develop quantitative theory. For a while, that's it. Thank you.
Thank you very much, Yuri. We have time for a question or two. If anybody would like to unmute themselves.
Oh, hi, Yuri. This is Bing. I have a question. And thanks very much for the nice review. It's excellent review. I have actually many questions. Probably we can discuss during the discussion session on Thursday. But today I just want to have a comment and a question regarding the Bunchen curvature model. The comment is that in the Frb case, different from the pulsar case, by definition, the bunches themselves cannot really provide Frb power. In order to provide Frb luminosity, one really needs to have a parallel E field to continuously pump energy to bunches. That is a requirement, I think is discussed in one of the Kumar papers. If that happens, then some of the pulsar situation probably needs to be reconsidered. I'm not saying that the magnet is working, but at least we should consider, for example, if the parallel E field is there, then there could be a balance between, say, radiation reaction force and acceleration force, so that the bunches themselves may not be easily distracted. And the second point is that the charges probably are separated. So there's the plasma effect, the naive version of the plasma effect may be reduced. That's just a comment. And the question is, there was a recent archive paper, I think by the German group, talking about this Bunchen mechanism. They actually showed that from numerical simulation that bunches can really indeed produce coherent radiation. So any comment you have on that paper?
Definitely, bunches could produce coherent radiation. The question is, what is charge of these bunches? And what is the energy of these bunches? The point is that bunches could not have energy larger than the plasma energy. At least, in reality, much smaller, because when wave energy approaches the plasma energy, it decays immediately. Therefore, in my view, producing strong enough, in pulsar situation, it is still possible because pulsar emission is relatively weak. But to provide power of Frbs, you need extraordinary conditions. I think they could not be met even in magnetar-magnetic sphere because we need extremely hot plasma, but in magnetar-magnetic sphere, cooling time of this plasma is few nanoseconds, just because this is bath of radiation. But of course, all this could be should be considered carefully. And in my view, formation of bunches is a very simple problem because it's 1D plasma. And everything could be just simulated. And it could be done, and people could see what are limitation of of the charge fluctuation obtained, for example, by two-stream instability. The problem is that nobody does this. Instead of people just very can't. I don't know why, because now such a simulation is not a big problem. But all our experience in plasma physics shows that all these fluctuations are small as compared with the plasma energy. And for Frb, this is extremely important because we need extremely strong fluctuations. To get radio emission from pulsars, it's enough to have fluctuations of the order of plasma energy, which is in principle possible, even though I'm not sure that this model is the best mechanism for pulsar radio emission, but by another reasons, more sophisticated. But for Frbs, I'm sure it does not work by large margin.
Okay, let's take one more question in this session from Zorawa.
Yes, so this reconnection model, are you aware that the integral result for SGR 1935's little burst shows that the radio comes before the X-ray peaks, at least the features in the X-ray light curve? Doesn't that sort of is inconsistent with the sort of a reconnection here?
I'm not sure because, first of all, this is Frb. Therefore, X-ray emission comes not only from the side of Frb, but also from the flare. Therefore, interpretation is not, in any case, the energy of the flare and even energy of the pulse that produces the flare is smaller than the energy of the flare itself. Therefore, it is a question how to single out the radiation from high energy radiation from the flare from total high energy radiation. Even though this is energy radiation helps to find parameters of the system because high energy radiation may be interpreted in much more straightforward way.
Okay, I think we should end it there. Thank you very much, Yuri, for this talk. And there'll be more time for discussion on Thursday as well. Let's take a 5-minute break and resume at, what would it be, 17:55, no, 18:55 CEST, or 12:55 here on the East Coast. So back in 5 minutes. Okay, well, thank you everybody so far for these great presentations. It's been a great start to this session, and we're going to wrap up today with 3 contributed talks, 10 minutes for each speaker plus 2 minutes of discussion. Our first speaker is Daniele Micili, and he is going to tell us about a search for periodicity in multi-component FRB profiles. Take it away, please.
Hi, everybody. I hope you can hear me well. This talk, on the contrary of previous one, is focused on a particular source. In fact, as Pragya showed in her talk, ChemFRB now released its first catalog with more than 500 fast radio bursts. And with such a large population, we are bound to find some fast radio bursts that show peculiar and interesting characteristics. And this is definitely the case for FRB 2019-1221. In fact, this fast radio burst is formed by a large number of single components that overlap due to a strong scattering that the source experienced. And these components make the fast radio burst extremely long, with a total duration of around 3 seconds. So first of all, we explored the possibility that this signal was actually caused by a galactic radio pulsar, but the dispersion measure that we measure for this fast radio burst is more than 4 times the maximum expected galactic contribution. And it has a relatively high galactic latitude, so we don't expect large variations in the model. And we searched the field that did not find any galactic regions that could explain this excess. So we consider this source to be extragalactic with high chances. I ran a fast Fourier transform of the pulse profile to get a power spectrum, and a clear peak at around 200 milliseconds was visible, which is a strong hint for a periodicity. But power spectra are not very good figure of merits for if you have a limited number of components. And so a proper time analysis was required. And as a first step, we had to model the pulse profile of the fast radio burst that you can see on the right plot. Now, this is not easy task since the components overlap due to the scattering. And so we used a simple model formed by a certain number of Gaussians convolved with exponential tails all with the same scattering timescale. We explored a large parameter space thanks to an MCMC fit, and we tried a different number of components. And with the fit, we calculated a reduced chi-square that you can see on the left plot as a function of the number of components used. And we chose 9 components, which is the smallest number of components with the lowest, that produces the lowest chi-square within the uncertainties. 2 things to notice is that with this simple modeling, we obtain an average width for the component of 4 milliseconds, which is pretty standard for fast radio burst, and a very large scattering timescale of more than 300 milliseconds that, as I said before, cause these components to blend. In this way, we obtain a time of arrival for every component, and we do a timing analysis where we fit only a period and the residuals that you can see on the right show a very clear periodicity at 217 milliseconds. So this is a smoking gun for a periodicity in a single fast radio burst. We tried the same analysis with other fast radio bursts. We didn't find any other that had a comparable or larger number of components. So we used these other 2 that you can see in the plots that had 5 and 6 components respectively. And from a similar timing analysis, we have some hint of a periodicity from the power spectra on the left plots, but the jitter in the residuals is pretty large, as you can see in the central plots. And therefore, the significance of the periodicity is not very large. We estimated it by simulating a large number of random time of arrivals and comparing with the periodicity that we measure, and we see somewhat higher values than 1 and 2 sigmas. So we consider these additional candidates as suggestive, but do not use them in the following analysis. We consider different possible scenarios that could account for the measured periodicity, and the first obvious one is an extragalactic radio pulsar. In fact, the period, width, and duty cycle of the fast radio burst is compatible with galactic pulsars, but of course the luminosity and the scattering timescales are extreme. If one of the leading model for the origin of fast radio bursts is, of course, magnetar, and if these fast radio bursts were generated by a magnetar, the detection of a periodicity would favor an origin from the magnetosphere co-rotating with the neutron star more than an emission triggered by a flare from the magnetar that is expected in a class of models. Now we explore, well, in this scenario, a train of pulses from an extragalactic radio pulsar is magnified from unknown reasons. And one reason that we explored is that a few pulses could be magnified by for a short duration of time by a gravitational lens. This could happen if a pulsar is in orbit with a black hole, and we consider a test pulsar at 1 gigaparsec distance with average luminosity. And on the plot on the right, we constrain the parameters of the system, and we need a supermassive black hole as companion, and the pulsar orbiting at around 10 parsec. So this is realistic, but cannot explain all fast radio bursts. But since similar fast radio bursts with similar number of components are rare, it's possible that a small fraction of fast radio bursts are produced through such scenario. We also consider different scenarios, such as quasi-periodic structures, so that these components are not strictly periodic, but are caused by a quasi-periodic phenomenon, such as magnetar crustal oscillations, or microstructures similar to those observed in bright radio pulsars and magnetars in our Milky Way. However, this is disfavored mainly for two reasons. The first one is that the periodicity here for the first source that I presented, the jitter that we observe is very small, and also by the fact that the pulse profile could be modeled with single components. For example, here on the right, there is a plot from Kramer 2002, where you see a pulse profile from Vela in the top plot, and single components that still need an envelope of emission. And here is the power spectrum for the same source, not as clear as in our case. Finally, we explore the possibility that this emission is actually not due to the rotation of a neutron star, but is the final stage of a neutron star merger. And so we are seeing the orbital periodicity there. This is more of an open question, an open discuss. So I leave this a summary of these four scenarios that we consider. If anyone has a different idea, feel free to contact me. The paper is about to be submitted in the next days. So thank you for your attention.
Thank you very much, Daniele, for these exciting results. We have time for a couple of questions. Anybody would like to? Yeah, Bing, go ahead.
Hi, Daniel. That's excellent results. Thanks. So for the neutron star pre-merger case, so you just have one peak that is multiple, one pulse with multiple peaks, or before this you have more pulses?
No, the idea is that the two neutron stars orbiting together will produce giant pulses. And there are a few mechanisms that have been hypothesized for this. And basically, the binary system would act as one single giant radio pulsar, if you will, where you see the beamed emission as it crosses your line of sight.
So this is not a repeater. So my point is that
okay, no, it's not.
Do we have a constraint on the repetition of this guy? For example, before this, probably you can have some tight upper limits. But what if in the future there's another one come out? Would that basically rule out this interpretation?
Yeah, absolutely. I agree with you. We haven't seen this fast radio burst repeating yet, but of course, if it does repeat, then this model is to be ruled out.
Thank you.
Yeah, thank you. A couple of other questions just coming in on the chat. Manisha asks whether there's a decrease in widths of the components with time.
We didn't notice any evolution in time of the components, but our well, due to the strong scattering and low signal to noise, our error bars are pretty large, so it's difficult to draw a similar conclusion.
Okay, I'm just going to ask one other question in the chat. I know that Zorowa has raised his hand, but Kenzie asks what the rotation measure of this FRB is and whether it's due to being gravitationally lensed by a supermassive black hole. Would you expect, in that case, a really high rotation measure like 121102?
Yeah, that'd be a very nice information to have, but unfortunately, we only have the total intensity for this fast radio burst. We didn't store the polarization.
Okay, that also answers Zorowa's question as well. Well, thank you very much, Daniele. This is really exciting. We have to move on to our next speaker. Calvin Long is going to talk to us about searching for lensed FRBs with CHIME FRB.
Thanks for that introduction. Can everyone see my screen?
Yes. Okay,
great. So hi, my name is Calvin, and today I'll be talking about searching for gravitationally lensed FRBs in the CHIME FRB sample. We're interested in the system where FRBs are used as backlights. And in this case, what you would expect is that a lens will warp the foreground spacetime and allow multiple FRB images to propagate to Earth. Lenses come in many shapes and sizes, and the observational signatures are different in different regimes. But in 2016, Julian Munoz realized that it's possible to use FRB sightlines as probes of compact dark matter. So today we're going to be talking about a search for lensed FRBs in the CHIME FRB data, and I'll be talking about preliminary results from this ongoing effort to discover microlensed FRBs. The phenomenology of gravitational lensing, as a quick review, is very rich, but there are basically 4 signatures, some of which are shown in this animation by Scott Gowdy. In this animation, you see that there's a lens in yellow, a transiting backlight shown in red, and the lensed images that we actually observe shown in blue. And there are multiple images is the first, one of the most important signatures, but also the image shapes are distorted. And if you monitor the system over time, the combined flux increases and decreases on the order, with a time scale on the order of the Einstein radius crossing time. And a fourth signature, which is not evident in this animation, is that because the images skewer different parts of the lens plane, those images are delayed with respect to each other. So if you time resolve this system, you would see one pulse than the other. Each of these observational signatures has been seen in different areas of astrophysics, from strongly lensed quasars to CMB weak lensing, to optical searches for microlensing in the local group. All I'm proposing to do is, with time FRB data, to directly search FRBs for signs of this multipath propagation with looking for a differential Shapiro delay between different FRB images. At this point, you must be wondering, though, why use FRBs? You can do this kind of science with any kind of transient. Why can't you just use gravitational waves or anything in the sky that flickers on and off? And so the short answer is that you absolutely can use your favorite transient. Some groups have done this for GRBs earlier this year, where they claim to have discovered an intermediate mass black hole from a lensed gamma ray burst. But the long answer is that there's a strong advantage to using FRBs to doing this kind of science. So as we've heard in talks from Pragya and also earlier estimates, FRBs are extremely common. And they also have shorter timescales than that of gamma ray bursts because of their possible association with magnetars as evidenced by SGR 1935. And so that already gives FRBs some of the fastest variability timescales in the night sky. So not only do you accumulate bursts quickly, you can also access short timescales for precise delay measurements. Another reason FRBs win is that in the same way that you can buffer voltage or electric field data for FRB VLBI or polarimetry, you can use that voltage data directly and the phase information there for an interferometric search rather than using the light curves. This decreases the timescales to which we can reach, and it has a direct consequence on the physics reach of our search, allowing us to probe lighter lens masses than previously accessible. And this is the search that I will be describing today. One picture that I really like to use to describe what we're doing is the following. The picture in your head should not be that we're taking two light curves and correlating them. You should be thinking that we're doing VLBI with a single telescope. And in this case, you don't have two independent telescopes on opposite sides of the Earth, but you instead have a baseline that's created by your gravitational lens, as shown on the right. So whereas incoherent time delay searches rely on morphology arguments to claim that a double pulse is really a lens and not a double peaked transient caused by complicated astrophysics, we can use phase information in the electric field and correlate those electric fields at nanosecond time resolution. And if it's truly coming from a gravitational lens, we would expect a double peaks transient to not correlate, whereas a gravitationally lensed system would absolutely demonstrate correlations. How our search actually works is that we get voltage data from every FRB that we detect, or a large fraction of them. We dechannelize that voltage data, which we sample at 800 megahertz. And so this gives us a time resolution of 1.25 nanoseconds. And we calculate a delay spectrum from that dechannelized voltage data. I've shown this with an x-axis ranging from 1.2 nanoseconds all the way to, well, our voltage data goes all the way to 100 milliseconds, but I've shown a small slice around lag 0. And a coherent lensing signal, what we were searching for, would show up as either an upwards or a downwards peak in the space, actually. You'll notice that there's some rich structure here, and a lot of our systematics can be visualized in this space. On the shortest lag scales, on time scales smaller than the size of the telescope, internal telescope reflections dominate and give us some of the structure at short time scales. On medium and long time scales, things like FRB scintillation and RFI contribute to the delay spectrum and give us statistically significant excursions from 0. And because coherent gravitational lensing has never been observed, we are still in the process of developing an exhaustive list of null tests that can be used to verify true candidates from false positives. So you must be wondering what we've seen so far. My honest answer is nothing yet, because the search and its vetoes are still being developed. We're testing on samples of 50 FRBs or so with baseband data from the first CHIME catalog and onwards. But we do have some idea of our sensitivity. And an interesting question to ask is that given our sensitivity, what do we expect to see as a function of the constituents of the local universe, specifically the dark matter fraction, and whether that could be made of compact objects. There's a well-known way to calculate this. For every FRB sightline, you draw a tube out to the inferred distance of the source. One day, when we have great localizations from projects like previously discussed, and also CHIME outriggers, which Jane will talk about next, we will have measurements of the redshift, so we will know the distance to each burst sightline. And this pencil beam has an annular profile. The inner edge of the annulus is limited by the time resolution of our search, and the outer edge is limited by the burst brightness. The white ring is the characteristic cross-section of the tube called the Einstein radius. And as you go to larger masses, both the characteristic timescale of the Shapiro delay and the Einstein radius both increase. So you essentially just need to calculate the volume of this annular pencil beam and make an assumption about what the local density of lenses is, and you can calculate the expected number of lensing events along this line of sight. One thing I wanted to point out at this point is earlier I said there's a correspondence between lensing timescale and lens mass. This is roughly true, but there's actually a subtlety here, depending on how my system is aligned. If I had a very misaligned system, I can have large delays and images with very different brightnesses. But if I made that system perfectly aligned, I could have very small time delay and equal fluxes without changing any of the masses at all. So you can see that reflected in our sensitivity. So here I plotted our sensitivity to gravitational lenses as a function of lens mass. You can see that at for light lenses, our sensitivity comes from our exposure to short lag or short time scales. And for large lenses, our sensitivity comes from long time scales. But there's not a one-to-one correspondence. Otherwise, these colored bands would all be vertical lines. The way to read this plot is as follows. If all the dark matter were made out of point masses of 1 to 10 solar masses, we would have a Poisson rate of 55% chance of seeing one along this single burst sight line. You can extrapolate this further and say with hundreds of bursts, we have a good chance of ruling out black hole dark matter over a wide mass range or detect it positively. The two asterisks here are one that we don't think that all the dark matter is made out of machos. Supernova lensing already rules out the fraction of dark matter being composed entirely of compact objects. So we will have to work a little bit harder to make the positive detection. And also, this is subject to mechanisms like scattering screens that degrade our sensitivity. At this point, I'd like to cut it off here. I'm at 10 minutes, but I'm happy to talk more about this if there's interest. I like to conclude by saying that we've developed a powerful, coherent time delay search algorithm that can detect subsolar mass compact objects. And we've processed tens of FRBs and in the process of scaling up the search with the help of close collaborators, Zarif, Daniele, who you just heard, and our faculty advisors, Matt Dobbs and Kyo Masui, my advisor at MIT. And I want to thank the broader CHIME collaboration for making such a wonderful experiment possible, and take any questions now. Thank you.
Thank you very much, Calvin. Really nice work. We have a minute or two for questions. If anyone would like to raise their hand or drop a note in the chat or just unmute themselves.
So the lensing, can it rotate the polarization angle?
We don't expect to, unless there's like a differential propagation effect between the two different lines of, between the two paths around the Einstein ring. You might see this if you had like a galaxy scale gravitational lens, but since we're looking for micro lenses, the deflection angle is on the order of micro arc seconds. So I don't think you actually expect a large difference in the rotation measure along the line of sight. And because the delays you're searching for is on the order of milliseconds, you can actually, you actually don't really expect a priori a strong difference in the delta DM either, because the path length is just a few light milliseconds.
Okay, thank you very much again, Calvin. We are going to move on to our last talk in the session. Jane Kaczmarek is going to be telling us about localizing FRBs with Chime FRB outriggers. So Jane, you should be able to share your screen.
Yep, thank you very much. Let's see how this, it's always more interesting than it needs to be. Share, and let's, can I get a confirmation that you can see my slides? Wonderful. Thank you very much for the introduction. And yes, my name is Jane Kaczmarek, and I'm a postdoc at the NRC, and I'm a member of the Chime FRB Outrigger team, which you've heard so much of so far. And you've heard even a couple references to what I'm going to be talking about today, which is the expansion of Chime FRB into what we are calling the outriggers. So with any Chime and Chime FRB talk, this is a large collaboration with many people, and the efforts of those people are easily shown in the results that we've seen so far. So these are some of the major collaborators that we are using, or that are forming Chime FRB. So I mean, it doesn't take much of a motivation of why to study FRBs. We've covered that a million times in many of our talks in our papers in the past couple of years, but why outriggers? Why is Chime FRB, who have been so, we've been having great success with the release of our new catalog. Why are we expanding it further? Well, as Pragya mentioned, Chime FRB, when it turned on, really did revolutionize the study of FRBs with our catalog for the first 500 sources now published and publicly available. So we are now entering a new realm of, and a new science regime of studying FRBs. So there's something that Chime is not maybe the best at, well, it definitely isn't the best at yet, and that is localization. We can see FRBs, sure, because we have such a large field of view on the sky, but there's a lot that we're missing without getting the host galaxy identification or redshift to our sources. So all future science, at least most of the future science of FRB, is going to require this knowledge that we don't yet have for the vast majority of our FRBs that Chime sees. So really, we only have maybe 10, 15 galaxy host identifications. And this requires 1 arcsecond resolution, give or take, right? Obviously better resolution would be even better. But even in that handful of galaxies that we've seen, we see a vast variety of galaxy classifications and environments that are possibly hosting the FRB events. So Chime FRB has a resolution of about an arc minute. So obviously we're not going to be getting these types of correlations to have a host identification for each event. So what is it that we need to do? We need to get Chime FRB to having a better resolution for these events. And here we are. That is how we're going to do this. We're going to do it with outriggers. Outriggers are going to be a network of VLBI cylinders, just like Chime, and they're going to be across North America. So our goal with the Chime outriggers is going to be to localize 1,000 FRBs to 50 milliarc second or better localization in 2 years. So with that type of localization, we will get the host galaxy identification. We can determine the location within the host, and we can measure distances to the host while using correlating with existing and future optical sky surveys. So what is an outrigger station going to look like? Well, it is going to look like a single cylinder of Chime. It will be rotated and tilted so that it's actually sharing the same primary beam on the sky as chime. So in the case of Allenby, which is kind of our local outrigger, it'll be tilted by just about 1/2 degree, where when we're talking about what Green Bank is going to have, it's going to be tilted quite severely and rotated to the point where it's going to be quite a massive or quite a tall structure in order to share the same sky. There will be 3 sites. Allenby and Green Bank are confirmed, and the 3rd site has potential to be Algonquin Radio Observatory. The longest baseline that we're talking about will be formed between chime and GBO, or Green Bank as I'll kind of refer to it as, and that's about 3,300 kilometers. So that'll give us that resolution goal that we're talking about. Now, how are we going to reach these goals? You can't do VLBI all the time for all of the sky, because we live in a real world where data volumes are something that need to be considered for this type of blind search. So the solution to this is actually going to have a triggered baseband dump at the outrigger sites. So the back end of chime is going to, or chime FRB is going to be working as it always has, which is to beamform on the sky and identify if a FRB has gone off or not. If it has, it will send a trigger to dump the ring buffer at the other outrigger sites. And then that data will be sent for processing at a local or at a central hub. And this has been shown to work a few times. Calvin, who we just heard talk about gravitational lensing, also led work using what we call the Pathfinder, which is the pre-chime telescope that also exists at the Dominion Radio Astrophysical Observatory in Canada, and chime to kind of do this pseudo VLBI system and triggering of an FRB. So this can work because the 2 clocks of the 2 systems are actually different. And while the baseline is only about 400 meters, we're still able to see that we have a coherent signal in the 2 polarizations, which is shown on the figure on the right. Now, what about on longer baselines? Tomas Casanelli and Pranav Sanghavi have actually shown that this can work for crab pulses between Green Bank and chime, and as well as between ARO, the Algonquin Radio Observatory, and chimes. And when we're talking about this, the type of instruments or antenna that are being used for these types of crab pulses and correlations, they are not at all like what chime looks like. At Algonquin, we're talking about a 10-meter dish. And what we have at Green Bank is actually something called tone, which is a kind of an array of dishes that are working to cover the same sky again as chime. So we are actually seeing a dip in sensitivity, and that is absolutely fine, because that is exactly what we are going to be expecting when we expand to the full outrigger system. We'll lose about a factor of 1 over 2 root 2 in sensitivity to what we can actually correlate on, because the outrigger cylinders will be smaller, but we've already shown that we can detect and correlate some of the brighter events in the sky. Now, how else are we going to reach our goals? We're talking about 50 milliarc seconds. The 3,300 kilometer baseline between chime and Green Bank will give us about 10 milliarc second localization precision. The shortest baseline, again, Allenby, what we're saying is our local site, will give us about an arc second. So that number, 1 arc second, is still extremely useful for science, because that is still capable of giving us a host galaxy identification, which is one of the big hurdles that we need to go over or to overcome in order to go into future FRB science. And so the priority for picking sites has gone into being an existing site and having knowledgeable local staff. Now, that is the exception to that is our local site at Allenby, but it's also easily accessible by me and other staff at the Dominion Radio Astrophysical Observatory. So it takes us about 2 hours to drive there. And we're actually able to offer that type of local support from the chime home base. So it's also worth noting that with the resolution of 1 arc second and the bandwidth of 400 to 800 megahertz and the same type of searching algorithm that chime FRB has, the outrigger station between DRAO and Allenby, or chime and Allenby, is going to be equivalent to all the best FRB hunting telescopes already existing. And once the other outrigger stations come online, it'll just get better. So what is our other hurdle of this type of project? Well, calibration isn't quite easy for VLBI at low frequencies, especially when you don't have a moving array or a moving telescope. So what are we going to do? Well, we've decided that we're actually going to go with pulsars. Pulsars are compact objects. They are all over the sky with a slight preference to be located in the galactic plane. But it's worth noting that we have an ongoing VLBA project to localize pulsars to better than 5 milliarc seconds, and they will be our primary phase calibrators for the outrigger system. And at any given time, we are actually able to almost have at least one pulsar that is bright enough in the beam of CHIME. So we only have a gap of a few, I think 10 minutes on an entire day where we do not have a pulsar or a calibrated system that will be able to do VLBI. So this is ongoing work and will form a new network of well-localized pulsars in its own right. Oops, sorry. And we're getting close to the end. So timeline. It's nice to talk about these wonderful things, but how are we going? Well, we're just between Q2 and Q3, or second quarter and third quarter. Allenby, the local site, is under construction, and Green Bank has started construction just last week. And we're aiming for first light at the end of this year and the start of next year between the two sites. Proof of that, this was actually taken 2 weeks ago at Allenby. The foundations are in, and we are getting ready to actually put the cylinder structure on top of our new foundations. That CCAN that you see there is actually going to house all of our electronics as well as our RRF room. And you'll see a similar CCAN at Green Bank, and that little white hut in the middle of a beautiful green field will be the same. It will serve the same purpose at Green Bank for the outrigger there. So that will be our RF room and all of our electronics. Things are happening. We have things on the ground. Progress is measurable. So in summary, FRBs are wonderful. We'll be able to understand even more about the universe when we have this high precision localization that will be offered by CHIME outriggers. The success of this project is going to rely on us overcoming a few obstacles that are quite unique to low frequency VLBI, but we have ways around them, and we've shown that our system works. So I would like to just say thank you very much, and I would be happy to take any questions.
Thank you very much indeed, Jane. It's a great way to conclude the talks. We have some time for questions. If anybody would like to raise their hand, unmute themselves, drop something in the chat.
They're all stunned.
They are.
Can I ask, I'm curious, so are you going to localize all of the FRBs?
So the goal is yes, we should be able to localize with the type of system and data rates that we're expecting. We should be able to localize about 3 a day if we are able to detect that many. Let's say 1 a day. Let's just be even more realistic with ourselves. But the biggest issue that we'll have with localization is, again, that hit to signal to noise that we're getting. Because we're only talking about a 20 by, well, in the case of Allenby, we're talking about a 20 by 40 meter cylinder, and at Green Bank, it's a single CHIME cylinder. So we're still talking about half the 1 over root 2 sensitivity loss. We should be able to localize all of those events that are that bright. So let's say CHIME gets 3 events per day. 1 of those is bright enough for us to cross correlate on long baselines. They will be localized, yes.
And thanks. And have you estimated out of which redshift could this be localized?
As soon as you gave that talk, I'm like, oh, I should actually look at that. My understanding, and Vicky, please chime in if I am off on this, is we will be sensitive to the same redshift range as CHIME FRB. So really around up to 0.5 is going to be our real limitation. So if we're trying to push to redshifts of 1, we're probably going to need H1 absorption or some other type of intervening or some other external information for these events.
Thank you.
We do have We have a few that go above DM of 2000 in the CHIME sample. So we might get a few out higher, but not as high as Anastasia wants.
Yeah, sorry.
We have a question from Kenzie, who asks if you expect all the calibrator pulsars to be in the field of view for long enough to have a stable pulsar position that's consistent with the VLBA position, or will there be additional systematics?
That is a wonderful question. Yes, we do. So one of the reasons we've actually gone to VLBA for this localization is that the solution that we get, the position that we get for these pulsars is going to be the absolute that we will then phase reference to. So that'll be good to about 5 milliarc seconds, and our total error budget for the entire outrigger system is about 50 milliarc seconds. So all of these pulsars have been picked to be bright enough to be able to correlate in a single transit, which is at a maximum about 10 minutes. Not a maximum, but an average about 10 minutes across the field of view. And also hopefully have low scattering. Again, low frequencies will kind of broaden all of these pulse profiles and make scattering rings larger. But we've tried to, well, we haven't tried, we have. We've observed these pulsars in such a way that we can also bin to the peak of the pulse at kind of VLBA or L-band frequencies, S-band frequencies. And we will be able to actually use that kind of that central peak of the pulse to be able to get that localization of these pulsars to within our target. But yes, we will.
Great. That seems like a good way to end the session. Thanks to everyone for joining. Just as a reminder, our second and final session is going to be this coming Thursday, July 8th, the same time window, so 1630 CEST to 1930. Thanks, everybody. Vicky and Bing, I don't know if you have any other comments, but if not, we'll see you all on Thursday.
Thank you, organizers.
Bye, everyone. Thank you for a really, really interesting session.
Yeah.
Thank you. Bye.
Look forward to Thursday.